Good morning, Praveen.
Hey, can you hear me?
Yes, I can.
Cool. Thank you.
Yep.
Uh, uh,
It'll be a little while before everybody shows up.
yeah. I just joined in case if there's any problem or not. Like I just wanted to check if I have any problem from my side.
Yep. No, that's good. It's better be early and safe.
Yeah.
All right. I'll be here if you need any support.
Sure. Thank you.
Yep. Thank you.
I mean, I'll get a notification, right, if any of the panelists are like joining.
So if you click down bottom participants,
Okay.
then you'll see on the right hand side where it has panelists and it lists you and I,
Yeah.
and then you'll see attendees on the next to that.
Yeah.
The attendees will start to populate as people show up.
Okay.
Now, are you going to be promoting people?
Um, I
Are
mean,
you?
in case if Dr. Burrs is like running late,
Mm-hmm.
so I might be promoting like the presenters.
Right. Do you have the list here?
Yeah, I have who's going to be there for the first session.
Oh, okay, great. I've been doing it in the past, but if you
Oh,
want to
okay,
promote,
okay, okay. I mean, if you're sure with it, you can do it. There's no problem. I was just asking in case if any of us are not
well,
available.
are
So
you the student helper or?
yeah, I'm the student helper for
Okay,
today's
great.
session.
So I may, if I have to step away for a moment here or there, I may just
Okay,
I'll private message you,
okay, sure.
and then at those times, if you could just keep an eye on the attendees, and if someone on the list shows up,
Okay,
so I already made you co-host.
okay, that's
So
great.
if you see it, when you hover over, like, let's say my name or the
Okay,
AJC webinar,
okay,
see the more button.
yeah,
When you click on that, right now it doesn't have much, but when it's on
yeah,
an attendee, it'll
okay,
say promote. One of the options will be promote to panelist.
okay, that's cool. Okay,
It's pretty self-explanatory once you hit that more button.
okay,
But I'll be here, and if in fact, let me send you this here. I'm gonna give you my cell phone number just to be in case,
okay,
and you can call or text if I'm not responding. But I
okay,
should be here for the duration. I mean, I may have to step away,
okay. That's not a problem.
and let's give my name as well with EIT.
Okay,
All right, great.
help. Yeah, thank you.
And it's pronounced Praveen.
Yeah,
Okay, very good. Well, thank you, sir. I'll be here. You can chat with me, or like down bottom with the chat, and then choose my name
sure.
um, if you need anything, or just speak up.
Okay.
All right. Thank you, sir.
Thank you. Thank you so
Yep.
much. Yeah.
Yep.
Morning, Dr. Burris.
Hi, Adam.
Good morning, John. How you doing?
Fine. So we have a couple of quick changes this morning, right? So we're going to go half an hour and then 2 hours and then the panel, okay? And there's no break. You have it, right?
I have the list of people I need to promote, so I'm in good shape. I'll be here for the duration.
But you got the last agenda, the last schedule.
Yeah, later last night, right?
Right, because there I have the academic panel. Okay, so that
Correct. No, I have that. Yes, I do.
Yeah, that's what I was worried about.
And I spoke with Praveen as well earlier, and if I have to step out, I'm going to let him know, and he can take over while I'm gone. But I should be here for the duration.
Okay. Hi, Praveen. How are you?
Okay. Morning, Dr. Burris. I'm fine. How are you doing?
Fine. So, hi, Gabriela. Is Yoan coming or?
Hi. Yeah, he should be joining quite soon.
Okay. Are you in Finland or where are you?
Yeah, we're both in Finland, located in Finland.
What part of Finland?
In Espoo, so
whereabouts is
close
that?
to Helsinki. It's still the capital area.
You're still south. Okay, fine.
Yeah, still quite at the south.
Not near the fjords, right? Yeah, but
no.
Okay, good. Okay. Can you hear me now?
Yeah.
Yeah. Okay. Because I had to change something on my speaker because it gets interference from the power cable.
No, it's fine now.
When it's charging, and that's why you hear this noise. Okay, good. So we're okay. So Gabriela, both of you are going to talk. Is that correct?
Yeah, that's correct.
Okay. So who's going to start? You or Yoan?
Yoan starts, introduces a bit us, and then I take the first half of the presentation, and then he takes the latter half.
Okay. So try to keep it to about 25 minutes, so we have 5 minutes for questions because the schedule is very tight.
Okay.
Okay, very good. Thank you. So I have about 5 minutes for Yoan. Here he is. Okay. Hi, Yoan. Good morning. Good.
Can you hear me now?
Yes.
I can hear you now. All right, thank you. Headset issues.
Yeah. It's electronic. It's called electronic dependence.
Indeed.
Hi, Rhoda. Good morning.
Good morning, John.
Are you usually an early bird, or are we forcing you to be early?
I think for a long time I probably am in East Coast time, so.
Oh, I see. Okay, that's right. Is Linda there or here?
She's here working.
You remotely with NSF.
Yeah.
I see. Okay.
So I think I go to bed with the West Coast time and I'm awake by the East Coast time.
Oh, that's tough.
That's what the body is doing. So.
So Jantao, I'll go for half an hour and then you will take over with the other session, right?
Yes, correct.
Okay, and we have already some of the speakers from the other session I see on. Okay, so.
Right, great. Thank you.
Yeah. Linan is on, Stephanie is on. Okay, so. Yeah. Good.
Hey, John, it's Adam. Real quick, just making sure you got the information on the recording from yesterday.
I haven't looked at my email yet, but yeah, we'll start
okay.
actually. We will start getting them down and putting some of them for which we have approval on.
Okay,
The ones we don't have approval, we're not going to.
that's fine. I just want to make sure you get what you need.
Yeah, yeah, right. We're checking with everybody again to make sure that, because people are, I mean, from far away actually are asking for. I got an email last night from Australia saying, you know, the times that you have the conference. The conference is great, but the times you have them are
Right.
are not feasible for
right.
for us folks down under. So if you could actually do one day delay posting, that'd be fantastic. And I said,
Yeah.
we're working on it, but I can't guarantee you anything. But you have they have the papers, okay? So the papers are online.
Sure. Well, I'll keep a copy of everything as well, just in case.
Yeah,
Just to be safe.
absolutely keep it, because we don't know how we're going to end up in the end. Okay?
Right. Very good.
And hopefully I'll get you the industry panel today or tomorrow morning, so we'll be complete. We now have where the conference is going to be next year, so we should be okay for the closing session. And Radha, keep in mind that I need input for the best paper.
Okay, yes.
I'll send an email, okay, because we need to decide about tomorrow evening. Right. Okay, I'll start. Hello, everybody. Good morning, and thank you for joining us. Today we have the fourth invited paper and lecture. It's going to be by two people from Nokia Bell Labs. They're both from Finland. That's one of the advantages of having, I guess, online conferences. They are by Yoan, Miche, and Gabriela Limonta, and the title is a data mining friendly anonymization scheme for system logs using distance mapping. So Yoan, you have the floor.
All right. By the way, speaking about recording, I think we couldn't get the permission for talk. So
I know that. Yeah.
All right, good. I think Gabriela, you can share the screen if it works. Yes, excellent.
Yeah, so it should be there now. Okay.
Yep, thank you. All right, so very briefly about us, because we're on a tight schedule. So my name's Yoan. I'm from the cybersecurity research team at Nokia Bell Labs, Espoo, indeed. And Gabriela Limonta is my colleague, and I'll let her take the first part of this presentation today.
Right, so hello everyone. Glad you can join us today. So my name is Gabriela, and today we're going to talk, well, Professor Barras already introduced us, but we're going to discuss our ideas around creating a data mining friendly anonymization scheme for system logs using a technique called distance mapping. So the key word here is system logs. So we're talking about logs, and why we're focusing on logs is, first of all, logs are everywhere. So if you think about it, they're in your data center, in the virtual workload containers, or anything running in the data center in the cloud. Not just the things in the cloud generate logs. Also, if you think of in terms of interconnectedness, all the base stations, access points, routers, all these things generate logs as well. And even one level further, all the connected devices, so cars, phones, computers, Industry 4.0, IoT applications, anything you want to name around interconnectedness, all of these devices and the applications running on these devices generate a huge amount of logs. So they become important when you want to analyze the system as a whole. So if you want to gain situational awareness of what's going on across your system. And the log entry is simply a record of an event or an important thing that happened in your system, so you keep track of it somewhere. And just to give some examples of what logs look like, although I'm pretty sure we're all familiar with what they look like. First of all, logs can be used to track what's called normal activity. So if we take a look at this, a log entry might be as simple as a timestamp and then a track of some web application running in port 8A7 tracks that it got a HTTP request from IP 10.1.1.1, and it was requesting the URL keys. And then this is for a web server. The server might track, yes, I received this request at this particular time, and I replied with a 200 status code. So logs are used to track all sorts of normal events in the system, but also you can use them to track errors. So in here we have an example of a log where some user tried to get root access in a machine where the user didn't have root access. So this is an important event or an error condition that you want recorded somewhere because you might want to investigate this incident. So errors or weird events are another thing that logs will catch. And finally, my favorite is the debugging purposes of logs. So this is where you might see some programmer writing printf debug testing test 1 2 3, or my program passed through here, or maybe not in this funny way, but these kind of event logs that are used for debugging applications. So lots and lots of logs that you would use when you try to find out what's happening in your application. And so logs, this huge amount of logs can be used for different purposes. And a couple of examples are around. So the first one is anomaly detection. So once you have this huge amount of logs, you can use data mining and machine learning to model what your system looks like, what your logs look like under normal conditions. So how your system behave, what your logs look like during normal behavior. And then you would be able to detect if you have an anomaly in that behavior. So for example, here, if you have a different phone connecting, or you have a phone requesting things that it hasn't requested before, these would be red flags that you might want to investigate. So logs can be used for this anomaly detection purposes. And another use for logs is failure analysis. So once you have, let's say, this device failed, you could do some sort of root cause analysis or other forensics to find out why this particular device failed by investigating the logs. And sometimes it might happen that if you trace back the logs for the failure, it might be a failure in a completely separate part of your infrastructure. So for example, if a service failed to start, or if somehow some other component along the dependency chain failed, that might cause a failure in an unexpected place. So having logs, you can use these to investigate these root causes and actually solve the problem. Then in this talk, we're going to particularly focus on the telecommunications example, and that's because telecommunication logs hold important information. So if you think about it, there's many interconnected devices, and the telco companies hold logs that contain information about location of these devices, movements between, let's say, access point and access point, what request the devices make, what are the usage patterns, and then all sorts of IDs of the devices. So if we think about phones, it could be the IMEI, the phone number, the IMSI, IP addresses, other sorts of IDs for the devices. So one big interest of telco companies is to actually monetize this data. They're sitting on this huge amounts of data, and how do they manage to actually get money for it? Because that's what businesses want. So one option is to use this data internally. So you do some data mining and you use the insights gained from that data to build better or even new services. You can use it to do network planning. You can improve the performance of the infrastructure or any other applications for these insights you get internally from using this data. But another huge interest is to actually monetize this data externally. So this means actually selling the data to third parties for any commercial purposes. That's where I guess the money is at. And of course, these third parties would use this data to help in their advertising, which is not our favorite topic, but it's something that happens. But it can also be used for urban planning or any other sort of planning where the telco data is useful. So it's not a new thing. We can see that there's been conferences dedicated to the whole topic of monetizing data from telecom companies. Oh, my presentation failed me, but this article actually says that this is a gold mine in the telco's backyard. So, and that there's two routes to monetizing the data from telecom. So this is just to discuss about how all this important information in the telco logs can be mined, and companies want to make money out of it. It's a legitimate interest. And it's actually not a new idea. So all the way back from 2013, there were articles like this where AT&T and Verizon will start selling your data. How do you opt out and things like that. And even not so long ago, from the beginning of this year, we had the same kind of news here in Finland, where Telia, one of the operators, was selling user location data for urban planning purposes. So it's not a new idea, and it's a thing that telco companies want to do. However, recently there's been this huge raise in awareness for privacy of people, which is great. And this has given rise to the creation of different data privacy laws. So for example, in Europe, you have GDPR, and in the US and California, you have the California Consumer Privacy Act, and Canada has this other law, the Personal Information Protection and Electronic Documents Act, which just rolls off the tongue. And similar to these, there's other countries that are passing their own data privacy laws. And what this means is that then telco companies or any other company that holds data really have to be very careful about how they monetize their data, because they could incur into huge fees for breaking a user's privacy. So for example, earlier this year, the FCC was actually giving fines to T-Mobile, AT&T, Verizon, Sprint, all these companies that were selling data back in 2013. They actually got huge fines for selling location data that had, from the data, you could personally identify people. So they were selling this data to, what are those, like debt collection agencies and to the police. So this is data that, for example, the police would need to get a warrant to obtain, and now they were obtaining it through a third party. So it's not great. And these privacy laws are increasing, which, don't get me wrong, I'm very happy about, because privacy is very important. So this means that we have to find a way to gain the insights from these from this huge amount of data in a way that preserves our privacy. So that's a huge motivation for this work. And well, there are several challenges in analyzing logs. The first one of them is the huge amount of logs there is. So if you remember that first picture I showed, all devices and all applications on the devices generate logs. So you have to somehow gather all of them. So it's impossible for one human to analyze them manually. We need computers to help us. Then there's the problem that application logs change from application to application. They are not the same. They don't follow the same structure. The log from my application will be different from the log from your application. Then there's a problem of the availability of open log data sets. So there's very few data sets that are freely and openly available. Because of this same reason, people don't want to share logs where there might be private information and then risk some fines or sharing something that they shouldn't. And this makes it very hard to, for example, train new machine learning models if you don't have the data to train them with. Then there's a problem of the lack of structure of log files. So many log entries are a timestamp and then a string that described what happened in a free form text. And well, that's kind of hard. This leads me to our last problem, which is transforming these text fields into what we would call machine learnable data. You can't just stick a raw log entry into your machine learning model. You need to somehow transform it into something that the model understands. So that is a huge challenge in log analysis. And I will let Yoan take the next part of our presentation. So
Yep.
Yeah.
Trying to share my screen now.
Yeah.
I hope you can see this properly. Yep.
Yeah.
All right. So coming up on what Gabriela was just saying, the common solution to actually make your data machine learnable, for lack of a better word, is to actually transform it into, call it Euclidean data or numeric data. I'll call it Euclidean for the rest of the presentation, but just imagine numeric basically data. So real numbers, integers, or something similar to that. And typically you put your data into RD, let's say. So you just try to use the same number of fields as you have originally in your log file, for example. And there are many problems with this. So you would first typically transform your data into numbers, like I was saying. Whatever is your data, you need to have it into a numeric format to be processable by machines to a large extent, at least by machine learning very often. So the question becomes, what numbers do you need to use, or what numbers can you use? Should you use integers? Should you use reals? In some cases, that option is very clear and very obvious from the type of data that you have. In other cases, it's actually very difficult to decide. So you might actually make an arbitrary choice there, which, well, might not cause problems, but it might. The reason it might cause problems is that you have many parameters to consider. If you start asking yourself questions about what values do I put on this specific log entry or this specific string, basically, or timestamp or something. The first one is that if you start using integers, for example, very simply, and you put a 1 on a specific log entry value and a 2 on another, then suddenly you've created a sorting order between your two entries, which was not there just before, and it might not even make sense. This is not an issue if you're the one person who's going to take the data, transform the data, perform machine learning on the data, and take out the result to some meaningful output. But if you're considering a whole pipeline of entities or even software components within a company, or even selling to external companies, like Gabriela was saying, you're actually transforming the data very specifically in such a case. And then you're going to pass this transformed data to the next person or the next piece of software, which has no idea whether this order is actually inherent to the data or you have created it arbitrarily. So it can be a problem, and in large corporations with many services, it obviously is a problem in our case also. The second parameter, I'm not listing them all, but just a couple that you have to consider, is that you're also creating an implied distance. Again, if you're putting specific value 1 for something in your log file, set an entry, and 2 for another, you suddenly created a distance of 1 between these two elements, which might be perfectly fine, or it might actually be very problematic. You have no idea on what kind of distance these two elements should be at, and you just created one such distance. And how do you arrange the distances between all elements or the like? This becomes, well, intractable questions in some cases. And for log files, it's a very non-trivial question indeed to answer. What this means is that basically you're creating a structure underlying all of your data. By assigning numbers, whether they're real or integers, you're going to assign a specific structure, an algebraic structure, I mean, in this case, on your data with a distance and a specific, well, technically a metric space of some kind for all the attributes that you're considering. Again, this might not be an issue in some cases, and I think actually in log data and in many cases that we consider in our company, for example, this is actually a problem, or this shows up as a problem. And how do you decide on all of these? These are so many questions to answer that it's very difficult and kind of uncomfortable to answer. So just as a practical example, for example, here using the log entries that Gabriela was showing before, the timestamp part is pretty straightforward. You can turn that into an integer by using just the Unix epoch, and then you can compute over that easily. You have a notion of subtraction, addition, and so on. It's not too difficult. This is quite an obvious case, let's say. But if we start looking at the string, which is our URL request in this case, it's get HTTP part, then how do you turn that into a number or some meaningful entity that you can compute over? No idea. Maybe you have some ideas, but it's not straightforward, and there's many choices to make. So this is why we want to actually look at distances instead of actually looking at the raw data and making these choices. So we try to skip the choice making part by using distances. And let's imagine that you have your original data logs for a second. I'll try to illustrate what we're trying to do at the moment in terms of research. So by the way, this is by no means finished research. It's just starting research in that sense that we are undergoing. So you have your data logs, and you need to transform that into a meaningful set of distances across all the different entries and across all the different fields. So your timestamp, your port number, your IP addresses, the app name, a string, a set of strings, doesn't matter. You have all these different fields. It's a difficult thing, and I'm not going to go too much into the details because this is part of a previous publication that we have published. We do something called distance mapping, which basically forces or transforms all these distances, not the data itself, but the distance between elements in your data, into a space that you can control. So typically you will want to do this and map to R2, for example, normal Euclidean space with the Euclidean distance, let's say in 2 dimensions, so that you can actually handle your data much more easily. But you only have the distances. You do not have actual points in that space. You only have distances between elements pairwise. So what you end up after this step, which I'll come back in the next slide very briefly, that's not the point of this talk really, but you end up with a matrix of pairwise distances, which is the usual tool that you can use for doing all sorts of things like visualization. There's many existing methods that take directly this distance matrix between points to perform some visualization. You can do outlier detection, like Gabriela was saying before, anomaly detection with this. It's pretty straightforward. You can do distance-based machine learning. These are all classical applications of this. What we propose here is to actually do re-embedding in R or RD. So let's say in R2 for the sake of just the fact that we are showing stuff in 2D. So you can then actually find sets of points in R2 in the 2-dimensional real plane, which are matching these pairwise distances that you have, so that you just create new points in R2 which are respecting this distance matrix that you have created using distance mapping. So basically, you're trying to find a way of representing in R2 data that cannot be represented in R2 because it's basically logs, and it wouldn't even make sense to think of this. And with that, once you have that, you basically have a set of data points, which are a sort of transformation into R2, preserving distances all across, which is the whole point of this technique or this idea, that you can use for any application that just takes normal numerical data, basically. So you can do visualization, you can do machine learning, you can do all sorts of things. Another exciting thing that we can do, and that is also the key point here of this whole work, is to re-embed the data in the original space. Now, what you will end up with is actually a set of log file entries, just like the original one, except you do this re-embedding in the original space in a way that you do not end up with the same values. You end up with something different. So just like you're creating points in R2 that are representing your pairwise distances, you do the same thing in the original space. This is a very difficult one that we're working on very much at the moment. It's work in progress. But with this, you can basically create data if you wish. You're making your data entirely private. It doesn't relate at all to your original data set doing this, except that it preserves the pairwise distances and therefore the relationship between elements in your data, from your original data. Sorry. So you're kind of achieving a certain notion of privacy by doing this, while preserving again the distances. Very briefly, why do we care about distances? I've said a few of these things already. So you can use distances directly for machine learning, or some algorithm like KNN and clustering algorithms are typically very happy with just using a distance matrix directly. And the reason we're doing this distance mapping approach is that I did it many times before by just assigning integers and reals in my career. And to be honest, when questioned by my colleagues or further people down the line about the data processing, the best answer that I had was that, well, you know, it's an art. We have to try and see many different values for the integers and adapt. And it was a very uncomfortable discussion to have, to be honest. So what we're trying to do is to avoid this discussion, avoid this set of choices that I presented in the beginning about finding which integers, which values are the best, and just jump straight ahead over that by using distances between points. So of course, we're not preserving the whole structure of the data. That's a given. We only preserve pairwise distances and therefore relationships between points, if you wish, or log entries in our case. Maybe I explain very briefly distance mapping. I think I planned for way too much content. So very briefly, because this is described in other papers, so maybe it's not very needed here. The point of this technique, distance mapping, is to make any distance function that you would have, so non-Euclidean typically really, over any metric space. So we need a metric space for this to work. That's the main assumption. And we want to make that distance function behave like the Euclidean one in a probabilistic manner. I'll skip very quickly, but basically the idea is to have the same probability mass for two specific distance values. What I mean is that if you're plotting on the left here, the probability density function of the pairwise distances in your original space, so the log file space, for example, for a specific attribute like the timestamp, you end up with a distribution that looks like this, say. And what you want to do is that the integral up to a certain value is actually equal to the integral of, well, in our case here, the Euclidean distances in R2. So this is what that basically looks like. And you're trying to find the value alpha in this, so that you are trying to find the distance between 2 points in R2, in this case, which has the same probability of happening in that space as the original distance in the original space of the log files. So this is a probabilistic distance mapping. It's by no way absolute, and it's very obvious from some of the results that we already have, which are published. But so far, that was the best one that we found. I'm going to skip a bit over the open question because I don't really have the time, and I want to go over one more slide at least before we finish. But there are many questions specifically about computational load. What is the best metric space that you want to map to? Is R2 the good choice? Is R3 a better choice? Is the Euclidean distance a good choice? Should you use something a bit, well, different? These are non-trivial questions which, of course, arise from the same problem as before. It's just translated to distances to some extent. But the questions are a bit less difficult to answer, and there's less choices to make, we feel at least. But I'm going to skip quickly. So about re-embedding, which is the last step that we want to do, and that's the novelty in the work we are trying to do at the moment here. So we have our pairwise distances from before, from the log file entry. We can do re-embedding in R2, as I said, and then we can do anything with the Euclidean data. we can re-embed in the original space and create basically a private version of the original data set. It will behave the same in terms of pairwise distances, in terms of how the points are distributed in space, if you wish, in terms of their relationship to each other, distance-wise, but the values are going to be completely different. And to be honest, they might not even make sense to some extent. So this is not meant for, this approach basically is probably not meant for a human user to actually look at and try to make sense of it, but more for machine learning algorithms, which are going to try to extract statistics or make clusters or groups. For example, for urban planning, this is very typically what happens. You need to make groups of people and how they move across a certain area. And you don't exactly need the details of, well, some specific IDs or properties of the location of people or their handsets or devices. You just need to be able to group them together in a meaningful way, and while keeping some notion of relationship between some people and how they move in time. Once again, I'll go a bit quicker. That was too much, but there are open questions with respect to this. So, for example, which space should you re-embed into? I've tackled a bit this one before. And an interesting one also, which we think makes a big difference here, is that we can probably actually generate more data, kind of in an oversampling manner, if you wish, not so much unlike bootstrapping in machine learning, so that we can probably use the pairwise distances distributions and just sample again from these to generate more points which respect the same distances between each other. That's under investigation, let's say. When we re-embed in the original space, there are some issues that come up. For example, are we going to make synthetic data that looks too much like the original? How do we control for that? How do we make sure that we avoid that? So that if we share the data down the line with a third party, we are relatively certain that it's different enough from the original data, and yet, again, the distances are preserved to a large extent. We also wonder whether outliers are going to be preserved and whether that's a problem or not. It's actually something we desire in the research we do, but for some applications regarding privacy, this might actually be a problem, and there might be solutions to this which are quite straightforward, actually. So to conclude, because we're coming up to the end, the point of doing this is to actually make log files, or let's say non-numerical data or partly numerical data, more precisely, actually usable for machine learning. And specifically in our case, distance-based machine learning, such as I said, clustering or nearest neighbor-based techniques. So the method definitely has a bias towards preserving pairwise distances and preserving orders in ranking across points, if you wish. So it's very good for these specific applications. We don't know whether it's going to actually provide any meaningful solution for other techniques which are not so much distance, which are distance agnostic, let's say a bit more. The idea is to add privacy using that re-embedding in the original space, for example, creating privacy in the data by just preserving pairwise distance statistics without using the original data, and hopefully generating new data with a similar information content with none or less, at least, of the privacy concerns that we would encounter by sharing the original data. Even anonymized, sometimes we all know that's not exactly a foolproof process typically. Initially, this distance mapping, if you look up for the paper, I can send the link or you can contact me. This was developed for calculating mutual information on non-numerical data, which actually we have good results with. So that technique at least works. The re-embedding part is the newer part of the work that we're currently investigating. And we believe that it's at least an interesting tool for data visualization. So making sure that you can actually see logs in a normal space or two. Finally, our next steps are basically answering some of these open questions. Some of them are very non-trivial, and I've only listed a few. And we would really like to be able to plot something meaningful from logs, which are absolutely unusable for plotting at the moment, and be able to show that this distance mapping can actually be used for log visualization as a first step following up. And I think that's it from our side. sorry, I went slightly over time. I believe you're still muted, Professor Barras.
Yeah, thank you very much, Yoan and Gabriela, for a very interesting talk and bringing these problems to this group. I posed several questions and there's one more. You may want to answer them afterwards. But the main one is that we have looked at these problems for distances. And we found that embedding to Euclidean space and Euclidean distances has lots of problems for these issues that you're trying to understand. The main one being is that if you try to use distance to somehow characterize similarity, there are better ways to do it by using dissimilarity measures that they are not metric, like Bregman divergences, what we use. And then you can actually translate these dissimilarity measures directly to probabilities of correct classification or clustering or misclassification. So I wanted to ask you if you have any comments on that.
I would only say that I haven't tried it. And the only way that when I talk about distance, sometimes that's a bit that's actually an incorrect word. Sometimes they are not distances at all. They're very approximate and they do not respect the basic axioms at all. So I'm using it in the abusive way here. And some of them we actually use dissimilarity metrics or dissimilarity functions actually between elements. But I haven't gone as far as what you were describing. So that's actually an interesting idea.
Because this has an additional advantage that it can be used with the same mathematics for both categorical, Boolean, real, complex, any type of numbers.
Yep.
And we have, I can send you some papers. We have in our work, actually with Christos Mavridis, who is in the audience, we have actually done some machine learning with these algorithms. And surprisingly, they work very well, despite the fact that this these measures do not satisfy triangle inequality and they are not metrics. Anyway, we can continue the discussion offline. I'm sorry to have to stop it here. This is a very interesting topic. One last comment I want to make as far as connections to game theory that I want to mention is that the moment you start looking at multimetrics in these problems, and the easiest one is robustness, then game theory comes in because game theory is a natural way to study robustness or multimetric problems. So that is how, at least I can see how these problems can connect to the core subject of this conference. Again, Yoan and Gabriela, thank you very much. We will move to the next session. So I'm giving the floor to Gentao.
Okay, great. Hello, everyone. Welcome to the next session on cyber deception. In this session, we will have 5 presentations on this exciting topic. Without further ado, let's welcome our first speaker, Omkar Thakoor from University of Southern California. Omkar, please, you can share screen and you can start when you're ready.
Hello, everyone. Good morning. I hope all of you can hear me. Please let me know in case there are any issues with audibility. My name is Omkar Thakoor. I'm a PhD student at University of Southern California. And today I'm going to be presenting our work on exploiting bounded rationality in risk-based cyber camouflage games. This is joint work with all of my collaborators listed over here. So let's get started with the motivation. So over the past years, there have been several major data breaches on quite a few large enterprises and also government agencies, which has prompted a critical need to have effective cyber defense solutions. And one of the emerging approaches to that end has been that of cyber deception. So here the goal is to deceive the attacker by altering the information they have on the network and thereby inducing them to attack less valuable systems. In order to deceive the attacker, one of the many approaches is to camouflage the machines and their attributes. So as an example, consider this network which has, let's say, 3 machines, and there's an attacker which is trying to attack one of the 3 machines. So let's say all of the systems have certain attributes or certain vulnerabilities. In this case, let's consider 2 attributes, which is a web server and an operating system. And let's say the three systems have three different web servers and operating systems as shown. An intelligent attacker, instead of just attacking one system at random, they first try to invest some efforts into reconnaissance, and they try to gain some information about the network. So let's say they try to probe system 3 and try to ask what is the web server and operating system that is running there. And the notion of deception is that instead of truthfully revealing this information, we can try to either hide or lie about this information so that the attacker doesn't quite know what is the system that they want to attack. In order to achieve this kind of a deception, there are several challenges. First of all, we need to be able to accurately model how the attacker's response is going to be. So that depends on several factors. First is what exactly does the attacker know about the network as well as the defender's strategy. Secondly, the attacker may have quite a few diverse objectives, which may or may not be directly conflicting to the defender's objective. For example, they may be after either financial gains, or they may be after security information, and those objectives will determine how they respond to our different strategies. And finally, given the information of the network and the strategy, their behavior in terms of whether they choose from the possible options rationally, or whether they are averse to risk environments and so on. These kinds of behaviors also determine what the response is going to be. Finally, there is a large number of configurations and ways to camouflage the network in many cases. And in this case, the solution space becomes pretty large, and it becomes hard to optimize a particular strategy from that solution space. And finally, we need to consider the constraints on the feasibility of such strategies in real life. There also may be certain kinds of costs due to deployment, maintenance, as well as hindrance to the performance for legitimate users. So we need to make sure all of these costs are also under an affordable limit. So given all of these challenges, the question that we want to solve is how should the defender optimally camouflage the network under domain constraints to induce the attacker to attack the less valuable systems? And to answer this question, we resort to game theoretic modeling. The key reason to do so is that it enables us to strategize against adversarial attackers. If we are able to anticipate the response of such an attacker, we can optimize our strategy to mitigate our losses. And when anticipating this response, we need to address questions such as whether the attacker is rational, or whether they exhibit bounded rationality, or whether there is risk aversion, and so on. So to do this, we use a Stackelberg game model, also known as leader-follower game model. And this is a good fit for any sequential setting, which is typically the case in the security domain. This is because the defender typically sets up the defense first, and the attacker has the opportunity to do some reconnaissance and figure out what the defense is in place. So previously, there have been lots of game theoretic approaches for several security domains, ranging all the way from airport security to wildlife security, and also more recently in various cybersecurity domains. In particular, there are a huge line of work involves allocating or scheduling the defense resources in space or in time, and a root model in these cases is the Stackelberg security games, also known as SSG. And there are some key differences with respect to these kinds of models and our model. First of all, the core defense action in our case is that of a camouflage, which is affected by how the other targets or machines are made to look similar or different from a particular machine. Whereas in SSGs, the coverage of a particular target is what independently gives it a particular defensibility. Secondly, due to a typically static view of the network for the attacker, the defender is restricted to pure strategies as opposed to mixed strategies, which are typically deployed in SSGs. And finally, because of the second difference, we need to adhere to the weak stackable equilibrium as opposed to the strong stackable equilibrium which the SSGs use. And this is because mixed strategies are crucial to induce or guarantee strong stack equilibrium, which we do not have. Okay, so among various different game theoretic models for other cybersecurity problems, I'll focus on one which actually deals with this particular problem that we have. And this model is known as cyber camouflage games, or in short CCG, which is a general sum game model for these kinds of problems. So one of the first key limitation of this problem is that they assume that the attack success is guaranteed. It is actually not the case, because we have this deception effect in place, and so there is a risk that the attack may fail. And secondly, they also assume that the attacker is rational. So in such a case of a risk environment, they are neutral to this risk and they just maximize their utility. It is not the case, as shown by one of the recent studies among several others, that humans tend to be risk averse. And so we focus on the cases where the attacker is risk averse, or in general has some bounded rationality. So here's the outline of the model. I'll start with the model itself, and then look at different spectrums of attackers that we can deal, and show some numerical results as well. So to explain the model, let's look at an example. So let's say we have these different machines in the network. In this case, I've considered 12 machines. And instead of considering web server and operating system and all these different attributes, for simplicity, let's just consider the operating system as the sole attribute which determines the configuration. So here I have 5 Linux machines, 4 Mac, and 3 Windows. And associated with these machines, we have values for the attacker and the defender. For example, for the Linux machine, if it is successfully attacked, the attacker is said to gain 5 points and the defender is said to lose 3 points. So these are the gains and losses of the attacker and the defender in case of successful attack of these machines. And then the defender wants to camouflage these networks in some way, these machines in some way. And let's say there are constraints that there is no way that a Linux machine can be shown to be a Windows machine. And also there's a constraint the other way around. So under these constraints, let's say the defender somehow shows these 3 Linux machines to appear as Mac machines, and similarly for these other machines as well. So this is what the attacker observes. Okay, so we have this mapping from the true types to the observed types, and we can capture this strategy via a matrix where each entry, let's say this one, represents that there are 2 machines of true type Windows, which are masked with Mac, which is what the attacker observes. And if you look from the attacker's perspective, the attacker sees these 6 machines that are Mac, and he doesn't know what are the true types of these. So the attacker has to choose choose a particular observed type and guess a particular true type in order to attack. So let's say here, if they guess the true type as Windows and they choose one of these 6 machines, then they're going to be successful with a probability 2/6. And similarly, we can determine the success probabilities for the other choices. And given this success probability, if they actually do get such a Windows machine, then they're going to get 9 points. So that determines their utility. And similarly, by replacing the attacker valuations with the defender loss values, we get the defender losses. And in particular, if we have a rational attacker, then in this case, the rational attacker will choose this option, which maximizes their expected utility. And in this case, the defender loss will be 4. So to begin with, we want to choose a strategy that that minimizes the defender loss. Assuming a rational attacker, because of the restriction to pure strategies, we need to play a weak stack equilibrium, which refers to worst case tie breaking, and this gives us a bi-level optimization. This formulation is similar to the previous model CCG that I previously mentioned, and so I won't go into the details. But the key result here is that there is a single level reduction available for this bi-level optimization, which is achieved by assuming an epsilon optimal attacker for a very small epsilon. This gives us this single level reduction, again, without going into the mathematical details, because this is not the key contribution of the work. I just want to mention that this variable gamma captures the defender loss that we want to minimize, and I'll refer to this later on. In some special settings, such as a zero-sum game, we show that the optimal strategy computation is still NP hard. And in another special setting, which we call as the unconstrained setting, where we don't have any constraints on feasibility or cost, we show that it suffices to use only 2 observed configurations to achieve optimality. And using that, we also show that there is a pseudo polynomial algorithm using dynamic programming, which runs in time order of k to the 4, where k is the number of machines. So let's come to the main contribution of this work, the first of which is to use prospect theory to address risk-averse attackers. So because humans typically exhibit risk aversion, this kind of a behavior can be modeled using prospect theory, which is what we use. So prospect theory suggests that this risk aversion can be explained by applying a transformation to all the payoffs, which are monotone and concave. So as an example, if these were the payoffs, which are normalized from 0 to 1, then these are some possible transformations. In particular, we consider a parameterized form of this type, where C is a normalization constant and lambda is what governs the degree of risk aversion. So smaller the lambda, higher the risk aversion we have. So in particular, if lambda is equal to 1, the payoffs are not transformed there as it is. And if lambda is lower, the payoffs are highly transformed. So this is for lambda equals 0.5, and this is for lambda equals 0.25. So under these transformations, this is the algorithm that we have. So we just sample attacker responses on some random strategies. And given this data, we compute a lambda star, which is a maximum likelihood estimator for the data that was observed. And given this lambda star, we transform the payoffs under our assumed parameterization. And with these transformed payoffs, we compute the MILP that we just saw. For this algorithm, we have an evaluation scheme where we fix some distribution of attackers. In our case, we chose a beta distribution with certain parameters, which are varied. And by sampling random attackers from this distribution and sampling their responses on the random strategies, we compute a maximum likelihood estimate lambda, which is used for the algorithm PT that we just saw. And then as a baseline, we compare it against a weak cycle by equilibrium strategy, which assumes rationality, so no risk aversion. And then we compare the average losses of these 2 strategies on the distribution that we had assumed. And so for these different distributions, these are the results that we see. So by looking at the variance and the mean of these distributions, we see that when the mean lambda is high, meaning there is high risk aversion, and when the variance is low, meaning the population is very homogeneous, so it's easier to learn, we see a huge loss reduction. In the extreme case, when there is not much risk aversion, so the prospect theoretical algorithm does not have any edge, and also the variance is high, so it's hard to learn the parameter. We actually show we actually see a loss over the benchmark. However, in human subject studies on a test bed, which is work under submission, we have seen reduction as high as 47%. Okay, so the shortcoming of the algorithm, as we just saw, is when there is low risk aversion or when there's high variance, and also if the parameterization hypothesis is incorrect. For example, if the true transformations are given by one of these green curves, which we call as 2 piecewise linear, then our assumption that the transformations are obtained via these red curves is actually pretty imprecise. So because of that imprecision, it's hard to learn a single parameter accurately. So under all of these cases, PT is not likely to perform well. So what we want to do is we want to optimize against a prospect theoretic attacker whose payoff transformations are unknown. So for these kinds of payoffs, if W are the transformations of payoffs V, which are the true payoffs, we must satisfy monotonicity and concavity. So we add these constraints to define the valid transformations, and we run a max secret minimizing algorithm against any kinds of transformations that satisfy these constraints. So we call this algorithm MMR, and we actually see that under the cases where PT actually does not do as well, we see a moderate loss reduction with MMR with respect to PT. So it's not necessarily as good in other cases, but in these cases, it's pretty good. And at the same time, we see a very low regret as compared to the PT algorithm and the benchmark WSE. Finally, we look at the case where we don't have any knowledge of how the bounded rationality is governed, whether it's through risk aversion or any other means. So we want to have an algorithm that is free of any modeling of the attacker response. And in particular, we want to look at strictly competitive games, which refers to all outcomes being Pareto optimal. This is one case where if the attacker deviates from rationality, it's always better off for the attacker because the outcomes are Pareto optimal. And this case is what we look at because previous approaches are pretty conservative, so they try to look at the worst case. So in these kinds of games, the worst case itself is rational, so they are not providing any benefit. And we try to get some guaranteed exploitation of bounded rational attackers in these kinds of games. As we had earlier seen, we had an MILP where this gamma captures the minimum defender loss. And so for a particular defender strategy, phi and attackers choosing observed and true types J and I, if this is the defender loss, then the loss reduction relative to the optimum, we want to make sure that this loss reduction is at least some parameter beta times the amount by which the attacker deviates. So what we ensure by doing this is that if the attacker is far from rationality, we ensure that there is high enough loss reduction. So this is trying to exploiting the bounded irrational behavior of the attacker. So by adding this constraint to our MILP, we compute the strategy, which is our algorithm Gebra. And we show that in these strictly competitive games where previous model P solutions don't show any improvement over the benchmark, we get up to 10% reduction for attacker being very less rational. So to summarize, we provided a refined model which captures the risk of attack failure due to reception. We showed that analytical results for computing the optimal strategy against rationality. And then we showed how hard it is, as well as an MILP formulation and a fast algorithm for restricted special settings. Finally, we showed how to optimize the strategy for different kinds of bounded rationality, one using risk-averse attackers with known parameterized transformations, one which is a robust variant which just minimizes the max regret, and finally also a strategy that tries to exploit arbitrary deviations from rationality. For future work, one could consider prospect theoretic modeling where the distributions are learned instead of just a single parameter lambda. And also one can try to incorporate the probability weighting function, which is a part of prospect theory in addition to the payoff transformations that we considered. And also we could try to look at the settings of partial information where the deception strategy is not fully known to the attacker. With that, I'll stop. Thank you so much for listening, and I'm happy to take any questions.
Okay, thank you, Thakoor. And we have actually several questions from the chat. Here from Dr. John Barris, and maybe John Barris can unmute and ask. Dr. Barris, I think you are unmuted.
I'm trying to kill my phone because it's going to be interfering. All right, so very interesting talk. I have several questions. The first one is there a formal risk-sensitive reformulation of Stackelberg games?
Sorry, I'm not sure I follow the question.
So, I have risk-sensitive control formulations, right? Where I add risk to my utility function. And one can think of prospect theory as a matter of fact, a special case of that. Mm-hmm. So I can do the same with games, where in addition to whatever are the metrics, I allow risks for both players. Mm-hmm. So the question is, we have a very rigorous formulation for risk-sensitive control. Mm-hmm. Do we have anything like that for risk-sensitive Stackelberg games?
Okay, if I understand the question correctly, essentially, I would say yes, which is because, so if you look at our algorithm that we use, all we do is we use this parameterized transformation. And so any Stackelberg formulation which uses certain payoffs V, we can just, so the payoffs are known in our case. So as long as the payoffs are known, we just apply.
Okay. I get it. Then the second question becomes more important now, is that in everything you described, you assume you know the payoffs and the parameterization of the Pareto of the prospect curve. What if you don't? What can you do if you don't?
Right. So basically, our the second point in the spectrum that we considered is a prospect theoretic attacker, where basically this transformation is not known. So meaning the transformation could be of this form, which is pretty different.
Yeah, but you still know the payoffs, right?
Yes. So
I'm saying, if you think of it this way, you may not know the payoffs, you may not know the Pareto, but you know that the people are risk sensitive, as you correctly point out. We know this from experiments. The point is, what can you do if you don't know these things? Or if you want to think about the question a different way, what's the robustness of your solutions to errors in the models that you assume for the payoff functions or for the parameterization of the prospect curve? Is there anything known in this direction?
I'm not aware if there are things that are already known, but I can propose a particular way in which we can just extend this approach. The way we can do this is essentially now we consider uncertainty in how these payoffs come by. So we added constraints on these transformations W.
Okay.
If these V's are also not known, we can just simply add more constraints on V to come from certain uncertainty sets. So as long as we have some information on V, we can add appropriate constraints, and just that will basically give us a larger uncertainty set on V cross W instead of just W.
Okay, thank you very much. Yes, I get it. Thank you very much.
Thank you.
Thank you, Omkar, and for a very interesting presentation. Our second speaker is Linan Huang from New York University. He will present his research on dynamic cognitive honeypots for self-deception.
Hey, I guess everybody can see the screen, right? So I made this video last night, and so I just play this, and so I will be able to have perfect timing and answer your questions in real time. So let's get started. Hello,
Lina, you may want to increase your volume.
Oh, sorry. Let me wait. Hello everyone, I'm Linan Huang from New York University. Today I'm going to present a topic on far-sighted vulnerability mitigation of lateral movements using cognitive honeypots. Cyber-physical systems are facing new security challenge from advanced persistent threats, APTs, that differ a lot from the primitive attacks. For example, primitive attacks are opportunistic. They launch a lot of attacks and then pray that someone will be the victim. Whenever there is a vulnerability, they exploit it immediately. On the contrary, APT have specific targets such as a database to obtain confidential data or the actuator to cause physical damage. To reach the target at the final stage, APT can go through multiple stages such as reconnaissance, initial compromise, privilege escalation, and lateral movements, which can last for years. These new attack features enable APTs to invalidate reactive techniques such as IPS and IDS. For example, APT can obtain the firewall setting during the reconnaissance stage to evade it. And also, stealthy APTs result in a high error rates of IDS. Therefore, APTs can enter the system, stays in the system persistently, and remain undetected. Then the main security challenge for the defender is that he does not know when and where the initial compromise and the lateral movement happens. We use the following example of cyber-physical attack to illustrate the security challenge. The cyber network consists of host and client computers. Some of them are in the DMZ as they have to interact with the external network. Assets generally include hardware, software, and confidential information. For example, a programmable logic controller, PLC, can be a valuable asset because once it is compromised, an attacker can control the industrial plant for the physical damage. An example is the Stuxnet virus. Due to the segregation of DMZ, which limit the attack surface, we assume that the attacker from the external network can only compromise the client or the host in the DMZ zone, but not in the internal cyber network. However, the attacker may still manage to compromise the assets by lateral movement, that is, to exploit the service links in the internal cyber network to move laterally to reach and compromise the assets. Here is an example timeline. At the initial state K0, the user clicks the phishing email and her client computer U1 is compromised. Then if he logs into the host computer H1 from U1 and enter the password, a hash is generated, and then it can be exploited by the attacker so that the attacker can access H1 in the future stages without the need to know the password. The hash value may have some time to live, and we assume that the attacker managed to compromise H1 and take full control of it before the hash value expires. This is still called the patch-to-hash attack. Since the attacker has compromised H1, he can share some Teams content on host H1, and once the user accesses it from, for example, U2, the attacker managed to control the user's client computer. And this is what happens in this two stage, and now the attacker has compromised H2 by this Teams share content attack. Suppose that a service session between H2 and H3 start at some time K0 plus 3. Then the attacker may successfully compromise the target node H3 from host H2 by remote service session hijacking. From this example, we see that the segregation only brings static security. So security at every static time does not guarantee security under a long period. To identify the attack path over time, we need to add these temporal links. Then we are able to see how the attackers managed to reach the assets from the initial intrusion over this long period. To formalize the idea of temporal links, we propose the following model of time-expanded network, which considers the user-host network at different stages as one network. The node side includes all the hosts and the clients in the network. The edge in the solid lines represent the service link at different stages, and the edge in dashed lines represent the temporal links. We assume the service link between two nodes happen randomly with the probability beta ij, and the node that does not involve in any service links is called idle at a stage. For example, this U2 at K0 is H3 at K0 plus 1. For the attack model, we assume that the initial intrusion happened only at a node in DMZ with some probability rho I. The attacker can exploit the service link beta ij with success probability lambda ij to move laterally. There can be various techniques to achieve the compromise, such as the ones that we have already mentioned in example, but there can be many others. One way to counter lateral movement attack is to apply honeypots. The traditional honeypots are applied at fixed locations on machines in segregated areas. Therefore, it can be identified by the advanced attackers that these are honeypots, not the real service nodes. So here we consider a defense scheme of cognitive honeypots where the defender reconfigures idle nodes as honeypots and apply honey links from other node to it with probability gamma ij. Also, we change the location of honeypots at different stages so that it will make it hard for the attacker to distinguish honey links from the service links. This is what we call the level of stealthiness. So the main goal is to find the optimal honeypot policy gamma star to minimize long-term vulnerability, LTV, but we also consider other security trade-offs such as level of stealthiness. The probability of interference is that the honeypot should not interfere with the normal operation, and also there's a cost for changing the location of the honeypots. We refer to the LTV, long-term vulnerability, as the probability that an attacker at the intrusion node I can compromise the asset J0 within $K stages. It means that an attacker reaches node J0 before the final stage, and also it's not trapped by the honeypot. Since the attacker is stealthy, the stage of the initial compromise K0 is unknown. So this honeypot scheme aims to provide proactive and persistent protection. That is to say, we don't know when the initial intrusion happens. But once it happens, we want to reduce the probability that our asset will be compromised by the adversarial lateral movement. So we can compute this $K stage vulnerability by induction. This first term represents a successful immediate compromise of the assets. That means that the compromise is finished in just one stage. And if it's not successful, there is still chance because there are still $K-1 stages left. And attacker may have already compromised some new nodes in the site V during his first move. Attackers may also try to compromise some nodes, but fails, and the site U consists of these nodes. For other nodes, there's no service link to compromise. So here we have to sum over all the combination of U and V, which is a lot of computation. Since the events of A can reach C and B can reach C are not independent, we approximate this term as a set of nodes by this union bound. Then we can have this upper and lower bound under a given policy gamma by the induction over stages from $K-1 to $K equal to 0. And at the boundary, this JZ is equal to GZ upper. So we omit the details on the computations, and we want to provide this following analysis of the LTV under two heuristic policy. The direct policy is to apply the honeypot deterministically from the initial intrusion in the DMZ to the honeypots. The indirect policy is random, but mistakenly exclude the nodes of initial intrusion. So these two policies are two extreme scenarios. The direct policy focuses on preventing the attack from entering the internal network, while the indirect policy put all effort in detecting and deterring attacks during the persistent lateral movement. He puts no effort in the first compromise. So there are some security questions that we asked ourselves. For example, how effective is the lateral movement for different lengths of duration time? What is the limits or the bounds of the vulnerability when the time window goes to infinity? And besides the honeypot's policy gamma, whether we can change the parameters such as lambda and the beta to help to deter attacks. So first, under the indirect policy, since there's no honey links from the initial intrusion node, we have zero probability of immediate capture, which lead to a non-decreasing vulnerability over stages. And then the target node will be compromised with probability 1 as the case go to infinity. And here we define this probability of movement deterrence, POMD, which is the probability that attacks fails to move laterally from the initial intrusion I to any other nodes. To increase the R, we can either reduce the success rate lambda of the attack or reduce the frequency of the surface link beta. However, these security measures will affect the usability. So the first one will increase the cost, and the second one will reduce the operational efficiency. With this R notation, we can compute the upper bound of the LTV long-term vulnerability by solving this first-order linear difference equation. This final term shows that the value increase exponentially concerning the duration delta k, and a decrease in the polynomial growth rate as the POMD is R increase. So we want to increase POMD by changing the parameter lambda and beta. But due to the usability trade-off, as we have just shown, we cannot just let R equal to 1 for perfect security, because that will make a system completely unusable. So here we aim to find the minimum POMD to mitigate LTV when the $k go to infinity. What we find is that the minimum is characterized by the threshold. And if this R is bigger than the threshold, then the limit of the upper bound is less than 1. If we further forbid the direct access of the asset from the initial intrusion in the DMZ zone, then the limit of the upper bound is 0, which means that we can achieve zero vulnerability for infinite duration, and it means it's a long-term security for the assets. For the direct policy, which applies honey links from the initial intrusion to the honeypots, this is a better situation than the indirect policy, but we find that the security is still not perfect. We found that the indirect incomplete segregation will lead to a positive vulnerability residual, TVR, as this $k go to infinity. And also, if the value of LTV is less than T2, it will always increase as the number of stages increase. So let's conclude and review what we have done for this work. First, we're considering a cyber physical attack scenario, which consists of initial intrusion from external cyber network, and the lateral movement in the internal cyber network, but finally for the damage in the physical network. Also, we have considered these two challenges of persistency and stealthiness. For the persistency, we found that the cascade of static security at all this time does not necessarily ensure dynamic security. Also, we cannot identify the entire attack path if we only focus on one stage or a short period of time. For the stealthiness, we just don't know when the attacker has entered our system, and we don't know where and when the lateral movement has happened. So that's the reason why we're considering time-spanning network. As a comparison, the traditional attack graph model show the causal relationship from the preconditions to consequence. So it answers whether the asset will be compromised, whether the vulnerability will be used. From the graph viewpoint, it is a problem of connectivity. However, exploiting the same vulnerability at different times can lead to different outcomes, and some vulnerability can only be exploited within a given time window, as we show in the example. Therefore, we use this time-spanned network to model the time-space relationship for an explicit attack path. So the question we ask is whether the asset will be compromised within a specific time, which is a reachability problem that can only be understand if we consider time explicitly. Finally, we analyze the long-term vulnerability and find out that first, the vulnerability is non-decreasing over stages. The more stage an attacker can stay in the system, the more likely he can reach and compromise the vulnerable assets. And second, we identify a critical threshold of compromisability. That is, if the probability of movement deterrence is above this threshold, we can achieve zero vulnerability for the assets. Third, applying the honeypots may not achieve perfect security, and positive vulnerability residue it can exist as the stage goes to infinity. And that's all for today's talk. Thank you for your attention, and I'm glad to take questions. Okay, any questions?
Any questions from the audience? Okay, maybe I can have several questions.
Mm-hmm.
Yeah, for the first one, you are talking about this cognitive honeypots. I was wondering what is the essential difference between the honeypots that we are usually talk about and the cognitive honeypots that you proposed in this work.
Okay.
And that this modeling about the cognitive honeypots lead to any different attack modeling in your game?
Okay, that's a really good question. So we can see on this page. So basically, the motivation for this cognitive honeypot, saying like the traditional honeypot has the risk of being identified because they usually applied on fixed locations and also on machines like in separated areas, not in these production systems. So there's the benefit of doing that, because if we're doing that, there's no risk. But also there's a trade-off, like if we're doing that, it can be more easier to be identified. So that's the reason that we want to introduce the honeypots in our systems. So if we want to doing that, we have to make sure that the honeypots does not interfere with the normal links. So that means that they have to be cognitive. So in this preliminary work, we use this. We assume that all these honey links are applied with this given probability, but we can also make this like a moving horizon approach, and considering this honeypot policy to be different for different stages. this will be the work for the next step.
Okay, great. Thank you.
No problem.
Any other questions from the audience? Okay, thanks, Lina, again. If no, then we move on to the next presentation. Our next speaker is Stephanie Milani from Carnegie Mellon University. She will present her work on how to enhance the power of deception in security games. Yeah, you can get started when you are ready.
Cool. Hi, everyone. There have been some great presentations so far. Thanks to all the presenters, really interesting work. So I'm presenting our work on harnessing the power of deception in attack graph-based security games. This is joint work of my collaborators from Carnegie Mellon, Renmin University of China, the Army Research Lab, and Perspective Labs. So let's get started. So as we all know, security is a serious worldwide issue involving defending important infrastructure, protecting endangered wildlife species, securing computer networks, and more. Most security scenarios involve a defender who allocates limited security resources to protect targets from adversaries. Attack graphs are a commonly used versatile modeling tool for security challenges in different domains. They can model the abstract state dependency and transition relations of any vulnerable system, including a city's road system and the topological structure of a company's computer network. Most existing work on attack graph-based security games assumes that the attack graph is given and unchangeable. Another commonly used defensive mechanism is defensive deception. In cybersecurity, a commonly used one is honeypots, where we're altering the appearance of targets to try to entice attackers to attack that particular target. Existing work on deception and security often does not consider attack graphs or ignores the defender's ability to also allocate security resources in order to mitigate attacks. In this work, we want to study the use of deception alongside the allocation of security resources on attack graph-based stack-overwork security games. So our contributions are as follows. So we propose a variant of the stack-overwork security game called an attack graph deception game, where the defender can take deceptive and protective actions on an attack graph. So in this model, the defender uses deception to modify the graph structure, and a less capable attacker may observe this modified graph structure during reconnaissance. We also propose a way to solve a particular subtype of attack graphs called layered directed acyclic graphs. So we propose a MILF algorithm to efficiently solve this class of algorithm or problems. And then we also propose a neural architecture search algorithm for general directed acyclic attack graphs. To our knowledge, this is the first use of neural architecture search in stack-overwork security games. And we conduct extensive experiments showing the scalability of our algorithms, and we show that our algorithms and the use of deception lead to significant increases in the defender's utility compared to baselines. So I'll go into more of our model and then talk about the algorithms that we use to solve this big game. So an attack graph deception game is a two-player game on an attack graph. The defender chooses her strategy first, and then the attacker selects his strategy after surveillance. Here, the attacker has a type that's drawn from a prior probability distribution. The defender knows the distribution, but not the exact type of the attacker that she's facing. So this type can capture different skills and knowledge possessed by different attackers. Like in cybersecurity, an attacker might be better at reconnaissance, so they have a greater chance of noticing honeypots and other camouflage techniques. So attack graphs succinctly represent an attacker's possible attack paths. There are many different types of attack graphs in the literature, but we focus on the state-based Bayesian attack graph. So here the nodes are states and the edges are actions that the attacker can take to transition to these states. Each edge has an intrinsic probability of success. So in urban security, each node can represent, for example, the intersection of a road network, and in cybersecurity, a node can represent the attacker's intrusion status, like the computers that he's already compromised. We also follow the common monotonicity assumption in the literature that attackers will not relinquish previously attained capabilities. So what this means is, for example, in the urban security setting, if an attacker reaches a certain building and moves to another building, he can't relinquish the capability that he's already sort of reached that previous building. So using this assumption, we assume that the graph is a DAG. As stated before, we're interested in kind of three classes of DAGs, bipartite DAGs, layered DAGs, and general DAGs. And we assume that the players share knowledge of potential attacker actions. So the attacker cannot take an action or perform an attack that the defender isn't aware of. So in our model, the defender's action space consists of two action types, deceptive and protective actions. So the goal of deceptive actions is to make attackers plan their attack with a misunderstanding of the game structure. So the defender uses her deception budget to perform three different classes of deceptive actions. So she can hide an edge with a cost specific to that edge. She can add a fake edge with a cost specific to that edge, and she can modify the perceived reward of a node with a cost per unit of change. So we assume that the deceptive actions only change an attacker's perception of the attack graph and do not actually modify the true underlying attack graph. So a hidden edge is not actually removed from the network, and an added fake edge is virtual, so attackers cannot actually successfully move along that edge. So to ground this in cybersecurity, a defender can hide edges by masking connections between physical machines, and she can add edges by faking network traffic or vulnerabilities. And then she can change the perceived rewards by, for example, manipulating outgoing traffic to make the machines look like something else. To deploy protective measures, the defender has a separate budget to allocate effort along edges. By doing so, she increases the chance that she will interrupt the attacker's attack. So in a cybersecurity setting, this can represent the amount of time spent monitoring an edge. And we assume that the probability that the defender will interrupt the attacker's movement on that edge is proportional to her allocated effort. So again, the deceptive actions only change the attacker's perception of the attack graph and not actually the underlying attack graph. So the attacker's strategy is as follows. After observing the graph induced by the defender's deceptive strategy and the protective strategy, the attacker chooses a pure strategy, which is an attack path on the perceived attack graph. So the attacker can either choose not to attack at all, or he chooses to attack, and that attack consists of a sequence of nodes or edges in the graph starting from an entry point. So to execute the strategy, he starts from an entry point and moves along the edges as planned until he fails or reaches the last node in the path. So there are three failure cases for the attacker's movement. One is because of the intrinsic probability of success of that edge. The other is that the defender interrupts his movement. And the final way that the attacker can fail is because the edge is actually a fake edge. And the game ends when the attacker's movement fails, or he reaches the last node along the planned path. And we assume that the attacker is best responding based on his available information and chooses a path that maximizes his total expected utility. So this is how the player utility is decomposed. So when the attacker executes his attack strategy, he receives reward or penalty at each step, and his total utility is the accumulated undiscounted reward or penalty. Since the perceived reward and perceived success probability governs the attacker's response, we only discuss the attacker's expected utility. So if an attacker successfully attacks a node or arrives at a node, he receives reward specific to that node. If the defender interrupts the attack, then the attacker pays a penalty. So in this game, we want to find the optimal defender strategy, assuming that the attackers best respond based on their perceived attack graphs. Here we have defender favoring tie-breaking. Now, our game model can be viewed as a two-stage problem. So in the first stage, the defender takes deceptive actions, and then stage 2 is a Bayesian stack over game. And we want to optimize the choice of deceptive actions in stage 1, and then find a strong Bayesian stack over equilibrium in stage 2. So in our model, we consider 2 attacker types for expository purposes, but our model can be extended to multiple different types of attackers. So the first type of attacker is called the weak attacker, which believes all of the deceptive actions that the defender takes. The powerful attacker believes no deceptive actions and is not influenced by deception in the defender. So more concretely, we can look at this example game instance. So the first figure shows the 2 different attacker types' initial best responses. So the red is the powerful attacker and the blue is the weak attacker. So in this first figure, this is the original game. The second figure shows what happens when the defender protects edge 1. So it changes the best response of both types of attackers. And then the third figure shows what happens when the defender applies deception. So here the defender is changing the perceived reward of node 2 on the right-hand side. And then the defender is also adding an edge, which is E3, and then hiding E4. So as you can see, the powerful attacker's response doesn't change, but the weak attacker's response does change. So the defender achieves better utility overall. So our main theoretical result is that the problem of finding the optimal deceptive action is NP hard, even in the special case of layered DAGs that we consider. And we show this from a reduction of the knapsack problem, and you can see the full proof in the paper. So now I'm going to move on to our algorithm contributions. So the first is a mixed integer linear program approach. So we leverage the insight that in bipartite DAGs, in the defender's optimal strategy, any edge that is added ought to be in the optimal path chosen by the attacker. Otherwise, the defender is just wasting budget on an edge that will never be taken. So we leverage this insight in our MILP. In our MILP algorithm, we enumerate all possible action profiles, and then for each profile, we solve a mathematical program that optimizes the defender's utility given some constraints. And we further extend this MILP to the layered DAG case by using backward induction to simulate the attacker's choice. And the details of this MILP can be found in the full paper. But I specifically want to talk about the algorithm improvements that we make. So we improve the scalability in 2 ways. So we first track the best solution so far, and then we add a constraint that says that the utility achieved must be better than the or equivalent to the best solution so far. This constraint speeds up the algorithm by rendering many MILPs infeasible, and we can efficiently decide the MILP's feasibility. Second, we build a 2-layer search tree where the first layer corresponds to the powerful attacker's choice, and then the second layer corresponds to the weak attacker's choice. We compute each node's upper and lower bounds, and we prune a branch if the upper bound is less than the lower bound of other branches. And the details of how we compute these bounds can be found in the full paper. So we've tackled the layered DAG case and the bipartite DAG case. Now we're interested in finding solutions in the case of general DAGs. So we propose a neural architecture search approach to tackle this problem. So the insight here is that we can divide the defender's actions into 2 categories. One, actions that change the graph structure, such as adding an edge, or hiding an edge, and then actions that change the parameter values, such as manipulating the perceived rewards or allocating protective effort. So because the attack graph is a DAG, we can naturally view it as a feed-forward neural network. So we can redefine the problem as a neural architecture search problem, in which we first use a search strategy to find a neural network structure, and then use machine learning techniques to optimize the parameter values. In our approach, we use a genetic algorithm to propose architectures, and then a modified gradient-based technique to optimize the parameter values and evaluate the solution quality of each architecture. So we cast the defender's utility as the objective function, and then we use the forward pass to simulate the attacker's decision-making process with backward induction. So we build a network for each attacker type based on their perceived graphs, and then we obtain the defender's expected utility by aggregating the utilities obtained from these different attacker types. So in this figure, you can see on the left side is the DAG that we're considering, and then the right-hand side has the corresponding neural network, where the UD is the defender's total utility, and then the two dashed boxes correspond to the networks for the weak and the powerful attacker. There are still a few challenges that need to be resolved, such as the attacker's deterministic path selection, as we discussed before. To address this issue, we slightly relax the assumption of a rational attacker. In the interest of time, you can check out exactly how we address these issues in the paper. So now we have experiments to answer kind of the following three topics that we're interested in. So we're interested in what the effect is of different deception budgets. We're also interested in the solution quality and scalability of our algorithms, as well as how the defender allocates the deceptive budget. So we should first show the results on the bipartite DAGs. So first, let's look at the effect of different deception budgets. So here on the left-hand side, we can see that as the number of nodes increases, the generally the utility also decreases. This result also shows that in the bipartite DAG case, as we talked about before, adding a single edge is typically enough to achieve the best possible solution, which fits from our results from before. So for algorithm performance, we compare our MILP and NAS approaches with a evolutionary algorithm baseline, and then also MILP without deception. So here we show that in general, the MILP is exhibiting the best performance, and also on the right-hand side, we can see that the MILP is scalable. So we're showing that as the number of nodes increases, the scalability of our MILP is reasonable. And finally, we show the budget expenditure. So as you can see, if you vary the deception budget, you can see that the defender actually never hides an edge in any optimal solution for bipartite DAGs. So adding edges seems to be much more useful than hiding edges. Additionally, as you can see, where with the changing target rewards, the changing target rewards is more useful when combined with adding edges. So in the interest of time, I won't go into too much detail with general DAGs, but you can see the results in the paper. And to conclude, our techniques can be applied to more general settings. For example, when the reward depends on the edge and not just on the node. Additionally, our NAS approach works for any differentiable function, and our MILP approach works if all the constraints are linear in the defender's predictive effort. Thank you.
Okay, great. Thank you, Stephanie. And it's time for a question. I think there are several questions raised by the audience. Yeah.
Oh, sure. Let me.
Yeah, and the first question is asked by Learning Lee. Oh, actually, there are more questions. The first question is asked by Dana. And
Oh, I see,
Dana,
yes.
yeah, Dana asks regarding the assumption that the defender can change attacker's perception. In many cases, it might be more realistic to say that the defender can attempt to change the attacker's perception, and that attempt may succeed with some probability. How do you think this might change your results?
Yeah, that's a good question. So I guess that could be captured by having additional attacker types, where instead of just saying that, with probability 1, like in the weak attacker's case with probability 1, the attacker believes the deceptive efforts, you can then have this, as you suggested, success probability attempt. I'm not entirely sure how that would change the results, but I think that's a really interesting direction to explore.
Okay, yeah, great. Okay, the second question is asked by Limonta. Dear Stephanie, your presentation is very interesting. What if the attacker thinks one stage more, meaning the attacker knows your computed optimal strategy that attacker have a better performance? In the end, do you reach equilibrium?
So I guess to make sure I understand the question, so are you saying that the attacker knows the computed optimal strategy, including the deception strategy?
I think maybe one interpretation, I think from my understanding, so like the attacker is acting as the leader. Instead of the defender attacker stackable again here, the framework becomes attacker, defender, attacker, 3-stage dynamic again as well. So this makes the game more complicated. And if this happens, that the attacker have a better performance, or in the end, how do you reach the equilibrium if the model is changed into this setting, if I understand it correctly?
Yeah, so I think in that setting, I'm not sure what the benefit of deception would be, right? Because if the attacker just gets to observe that, then he can sort of say, well, I already know that this edge is fake, so I'm just not going to take this. So I think that the attacker would indeed have better performance, and the effective deception would be very little, if any.
Okay, great. Okay, so that's 2 questions from the audience. And thanks again to Stephanie for the very interesting presentation. Yeah, and we will move to our next speaker, Abhishek Kulkarni from Worcester Polytechnic Institute. And he will present decoy allocation games on graphs with the topologic objectives.
I'll assume that the slides are visible.
Yes.
So, thank you. So, hello everyone. My name is Abhishek Kulkarni, and I'm a third-year PhD student with Professor Jifu in Robotics Department at Worcester Polytechnic Institute. In today's presentation, I'll discuss our work on synthesis of deceptive cyber defense with temporal logic constraints. And this is the work that we have done jointly with our collaborators, Juan Lu, who was a visiting scholar at WPI, and Charles and Nandy from US ARL. So, as the sophistication level of the attacks has increased manifolds in the recent times, the role of cyber defender, which is to protect the critical infrastructure, has become notoriously difficult. Naturally, we need more sophisticated defense strategies that can run in real time and are both effective and robust. Now, most attacker-defender interactions are known to occur with information asymmetry, and usually the attacker is known to have an upper hand. So to rebalance these information advantages, the ideas like moving target defense and deception have been introduced in cybersecurity. For instance, various deception techniques are being used to protect cyber-physical systems from sensor or control attacks, or to protect industrial control systems like SCADA. The idea behind deception is to control and manipulate the disinformation to the attacker such that the resulting actions of the misinformed but still rational attacker are in fact advantageous to the defender. And this often imposes a cost and performance penalty on the system, which brings us to the same point that it is important to assess the effectiveness and robustness of deceptive systems, especially when we want them to satisfy complex security objectives. In addition to deception, it is also important to have dynamic defense actions to engage on an ongoing attack. So as Georgiev et al. Discuss in their work, such actions could include shifting the request to a different virtual machine or restarting a server, etc. Hence, another important challenge that we try to address in our work is to find an optimal way to combine these dynamic defense actions with deception to achieve optimal defense outcome. So in this work, we draw from different ideas studied in security games with payoff manipulation, incomplete information game theory, and most importantly, formal methods. From security games like those studied by Thakoor et al. Or Durkota et al., we borrow the idea of payoff manipulation. But instead of representing the payoffs as cost or reward functions, we represent them using linear temporal logic formulas and a labeling function. I'll introduce these concepts in upcoming slides. But this essentially allows us to reason qualitatively about the outcome of the game without having to worry about finding an expert or learning these unknown functions for the attacker. From the incomplete information game theory, we borrow the idea of hypergame model, which was introduced back in 1977 by Bennett. This model is different from Bayesian game models, which is commonly used to represent the attacker-defender interaction. For example, both Carroll's and Huang Zhu's papers use the Bayesian game model to model a game in which the attacker has incomplete information about the game. Now, one important advantage of using hypergame model over the Bayesian game is that it does not require the so-called consistency of priors, which states that the set of possible types of the player is a common knowledge. And lastly, from the formal methods, we borrow the notions of show-winning, labeling misperception, and compositional synthesis, which essentially allows us to provide provable guarantees about the decoy allocation as well as the defense strategies that we synthesize. So with this work, let me introduce the game model that captures the true interaction between the attacker and defender. Many of us might recognize this model as a two-player turn-based zero-sum game. So in this model, the state set S is basically partitioned into defender states, which are shown in the circles, and the attacker states, which are shown in squares. Each state can be understood to represent a configuration of a network, like which hosts are decoys, which servers have databases, etc. At their respective states, the players choose an action from the set A to change the state, that is, to change the configuration of the network. At a circle state, the defender can choose a defense action, such as restarting a server or moving a database to another server. At a square state, the attacker may choose an action, such as exploiting some SSH vulnerability. Now, the components AP, which stands for atomic propositions, and L, which stands for labeling function, allow us to reason about the properties of interest. Atomic propositions are in fact the system properties that we care about, and they essentially evaluate to true or false. And a labeling function maps a given state to a set of atomic propositions which are true in that state. For example, if we define decoy as an atomic proposition, which states whether a given state is a decoy or not, then a labeling function would, let's say, applied to a state A, will not contain decoy because A is not a decoy state. But when the labeling function is applied to G, then it will contain decoy. So let's see an example. Consider a label of a path shown here in the green, which goes from C to F to K to O. And suppose that O is a final state or a critical state that attacker wants to compromise. Now, by looking at the labels of C, F, K, and O, we can say that the attacker successfully compromises the critical asset. Whereas if you look at the red path here, which goes from D to E, which ends in a label of E containing decoy, we can say that the attacker has reached a decoy and thus defender has won the game. And the last component of the game is phi, which represents the objective of attacker given as a linear temporal logic specification. So let's take a look at what LTL is. So linear temporal logic is an English-like formal language that we can use to describe temporally extended security objectives in a succinct way. So continuing the example from the previous slide, a typical security objective for a defender would be to ensure the safety of the critical states. That is, we want to avoid any path that reaches N or O. Using LTL, we can write this simply as the first formula here. In LTL, we read this as always not N and always not O. Similarly, a lateral movement could be captured by using the second formula, which requires the attacker to visit O whenever the state F is visited. That is, any path that goes from F to J to N is not winning, even if it reaches a final critical state. And this can be written in LTL as always F implies eventually O. In general, using LTL, we can talk about different reachability, safety, recurrence, or persistence objectives, which is quite powerful. So this sets the stage for me to discuss the key question that we address in our paper more formally, which is, given a graph modeling the attacker-defender interaction, how to allocate up to K decoys so that the defender has the maximum possible range of protection. Now here we understand the range of protection as a winning region. That is, from every state within the range of protection, the defender has a defense strategy to ensure the satisfaction of her security objectives given an LTL formula. So let's see an example. So recall that in the game graph, the circle states are defender states and the square states are attacker states. And the states N and O are the critical states. So now if the game starts at state A, then it is very easy for the defender to see that at state B, to select the action going back to A and keep the game within this loop between A and B. So the security specification of the defender would be always satisfied. However, the situation is not so easy for the remaining states. In fact, we can show that no matter what defender does, attacker can guarantee to win the game from any other states except A and B. But what if defender can place the decoys somewhere in this region and in addition also find a strategy that ensures the game would reach one of the decoys? Then clearly the defender might be able to protect the critical states. But this means that we must synthesize two strategies instead of one. The first one is a decoy allocation strategy to decide where to place the decoys, and the defense strategy to decide how to drive the game into that decoy. And to add to our misery, the two strategies are in fact interdependent. For instance, observe that defender at state F. If we place a decoy at state K, then at F, defender's strategy must choose the edge going to K. But if we place the decoy at state J, then at F, the defender's strategy must choose the location, the edge going to J. So now we can talk about how the attacker's misinformation about decoys is captured in a hypergame. So first recall that by applying the labeling function on a state, we get back a set of atomic propositions which are true in that state. So to capture the attacker's misinformation, we equip defender and attacker with different labeling functions such that the attacker's labeling function never includes the decoy. Otherwise, it's identical to L1. So now we land in a situation where two players have different labeling functions and therefore they have different subjective views of the game, which essentially gives rise to a hypergame. In a hypergame, different players are allowed to play according to different subjective views. The game from the perspective of defender is shown in the blue bubble, and that from the perspective of attacker is shown from the red bubble, and they only differ in the knowledge about the decoys. But in fact, the defender has a higher order information. That is, we assume that the defender is aware that attacker does not know about the decoys. And this is essentially amounts to defender knowing both the subjective games of the attacker and the defender. which results in this updated blue thought bubble, which contains both the games of attacker and defender. Such a model is called a second order hypergame because in this case, one of the players, which is defender, has a second order information. So how do we solve such a hypergame to synthesize a decoy allocation and defense strategy? The broad idea here is that before making a decision, the defender would reason about how a rational attacker would respond to her action, given the attacker's subjective view of the game. And this idea is essentially captured in this block diagram. At the deceptive planner stage, the defender chooses her next action based on the knowledge of the true game and the subjective action. The attacker then proceeds to make a rational choice given his subjective game, and this process repeats. So now let us understand how the defender can reason about attacker's rational choice. To do this, we use the solution concept of subjective rationalizability from hypergame theory and use it to extend the notion of sure winning strategy in formal methods from complete information games to incomplete information games. We call this new solution concept as deceptively sure winning strategy. And the idea behind this deceptively sure winning strategy of defender is to assume that the rational attacker would select any action that he considers to be winning in his subjective game. For example, in the game on the left, consider state C. The attacker will perceive any action except the one going to B to be rational for him. This is because once the game reaches B, the defender can indefinitely restrict the game to states A and B. However, in reality, only the actions that go to F and G are rational because the attacker is unaware of the decoy at H. So if the attacker chooses to go to H, he would be in for a surprise. Excuse me. But unfortunately, placing a decoy at H does not help defender much. She still cannot guarantee in any way that the attacker will eventually end up reaching a decoy. But consider what happens if both G and H are allocated as decoys. Still, from C, defender cannot guarantee that the attacker will reach a decoy. Now, one might be able to argue that the likelihood of reaching a decoy has increased from C, but note that we will need more information about attacker's decision process to make such a statement. But now take a look at D. Defender can, in fact, from this state, D, say with confidence that no matter what action attacker chooses at D, the game will definitely reach one of the decoys. And we call such a state D as a defender's deceptively sure winning state, and the collection of all such states as her deceptively sure winning region. Thus, to answer a key question, all we need to do is to find an optimal allocation of decoys such that the size of deceptive sure winning region is maximized. In other words, this deceptive sure winning region represents the range of protection. Unfortunately, the story doesn't end here. Now consider if we have n possible states to place decoys and a budget of k decoys, then we must search a combinatorially large space to find the optimal allocation. Now to address this challenge, we turn to the idea of compositional synthesis from formal methods. Intuitively, what this means is that we place a decoy at k and compute the deceptive sure winning region, and then separately place a decoy at H and then compute the deceptive sure winning region. And then we compute a deceptive sure winning region when both H and K are allocated as decoys together by somehow composing these two blue regions. Now note that this compositional operator U plus is not the same as the set union operator, but instead it is nothing but a polynomial time algorithm to compute this. And in general, the set union of two smaller, or like the two smaller blue regions to the left can be shown to be a subset of the actual deceptive sure winning region on the right. This brings us to one of the key insights of our paper. The first statement, the statement A here, essentially captures the subset relationship that we just discussed. That is, as we add newer decoys, the size of the deceptive sure winning region will only increase. But more important are the sufficiency conditions that tell us when the problem can be reduced to a submodular or a supermodular problem. So suppose that the rectangles here denote the winning regions when different sets of states are allocated as decoys. For instance, if we allocate D union S1 as decoys, then all the states in green and red region are winning, so on and so forth. So what above theorem states is that the purple region is, what the above theorem states is that if the purple region is empty, then we have submodularity. And when the dark green region is empty, then we have supermodularity. And in both these cases, we can use these conditions to come up with an incremental polynomial time algorithm to construct the deceptive sure winning region. And so here is how the iterative algorithm works. For example, if we want to allocate 2 decoys, in the first iteration, the algorithm will compute deceptive sure winning region for each of the single allocation of decoys. So it will place a decoy at C and check the size of deceptive sure winning region. It will place the decoy at D and check the size of deceptive sure winning region, and so on. Suppose the decoy at state L results in the largest sure winning region. Oops, sorry. Then in the next iteration, the algorithm will end up computing the deceptive sure winning region for all the pairs, L, C, L, D, and so on. And the pair of the largest winning region will be selected. The algorithm terminates when either all the K decoys have been allocated, or when by adding a new decoy has no effect on the size of winning region. So in conclusion, we have shown how to synthesize a decoy allocation strategy and corresponding deceptive defense strategy for a class of incomplete information games in which decoys are used as hidden traps. As a result, the defender can trap the attacker into engaging with decoys with provable guarantees on the security of the system infrastructure. Now, there are a number of interesting directions that we can explore from here. So first one is like there are different types of deception, such as hiding the real or showing the false. This paper, in fact, addresses one part of the hiding of the real. So we can investigate how we can synthesize these both decoy allocation and the defense strategy in different types of deception. Yet another direction is to investigate deception under repeated interaction. Because the attacker will learn some new information about the game every time the attacker attempts and fails. And this could make some of the decoys ineffective. So the question still remains on how to modify these allocation and defense strategies to prevent such a thing from happening. And with this, I'd like to thank my advisor or collaborators in DAPA for their support and for everyone for tuning in. So I'll be happy to answer any questions. Thank you.
Okay, great. Thanks, Absh. And we have a couple of questions from the audience. The first one is from Monica. Hi, Abhishek. Thanks for your wonderful talk. I was wondering if there is cost associated with placing a decoy, and how does the method decide how many of them to use?
Okay, so that's a good question. So in our case, we do not consider the costs of explicitly placing the decoys, except that we just limit the number of decoys that you can place. So we start with the budget of K decoys, and we ask the question that what is the minimum number of decoys? Essentially, if you look at the algorithm, it incrementally keeps on adding the decoys until either you exhaust with your budget of decoys, or you find that no longer, like adding a decoy no longer gives you any benefit. So basically that's it.
Okay, great. And there's also a question from Learning Lee, and yeah, I think Learning can answer directly.
Hello, can you hear me?
Yes, we can hear you.
Okay, so I just want to ask, you have shown that the composition of two decoys of two individual decoys is a subset of the subset of the two decoy placement, right? So my question is, like when you keep adding the decoys, how much the difference between that deceptive sure winning and also the subset of that deceptive sure winning region?
Well, that's a good question. So it's in fact very difficult to say theoretically what, or give a number or a bound on how much is that difference. But in most of the experiments that we have ran so far, this difference is not much. So typically the subset, if we compute the set union and we compute the true composition of both the component deceptive show winning regions, the typical difference is pretty small. So it's in the range of like lesser than 10 states. And just to give you a context, like these experiments I've run by using some randomly generated graphs. So to answer precisely, I think we'll need to conduct more experiments on more realistic systems.
Thank you.
Mm-hmm.
Okay, any other questions from the audience? Great, thank you, Abhishek, again. And we'll move to the next speaker. Our next speaker is Alan Singh from University of Wisconsin-Madison. Alan will, in his presentation, Alan will argue that why popular imperceptibility measures in visual adversarial attacks are far from human perception.
Hello, everyone. Can you see my screen?
Yes.
Okay. So let me start. Thanks for introducing me. And my co-authors are Jiaojin Zhu, Erin Marshall, and Robert Nowak. We are all from the University of Wisconsin-Madison. Here is a brief outline of my presentation. I'm going to briefly introduce the problem we're tackling here, followed by the study we perform. Next, I'll talk about the experimental setup and the results. And finally, I'm going to conclude by discussing our findings. So it was shown in 2014 that adversarial attacks can be performed on deep neural networks. In these cases, a neural network that is an image classifier can be fooled by modifying an image that is correctly classified by the network slightly, such that this modified image is actually incorrectly classified by the same neural network. Here, the goal of the attacker is to classify the modified image X differently than the original image X0. Also, this change from the original image to the modified image needs to be small. The reason behind the second goal is the assumption that small perturbations are imperceptible to humans. Here, D is a distance metric according to which we are calculating this distance between the original image and the modified image, and epsilon is a threshold under which humans cannot detect the change. In literature, the most popular measure is pixel p-norm. We surveyed 32 papers, each with over 100 citations, and found that 27 of them used pixel p-norms. Unfortunately, 20% of these papers do not provide any evidence that pixel p-norms are a good surrogate to human imperceptibility measures. 50% say that they are just following other papers that use pixel p-norms, and the remaining 30% do not give any justification. As you can imagine, an incorrect measure of human perception can lead to some perceptual mismatch, which can lead to some other additional issues. So here's an example of potential issues happening. The green odd shape here represents a human's imperceptibility region around an original image X0. The gray rectangle presents a particular distance metric along with the threshold epsilon. As you can see, two types of error can occur here. First, there's a type 1 error where the humans perceive a modified image to be the same as x0, but the attacker thinks otherwise. In this particular figure, that is x1. Similarly, a type 2 error can also happen, where an attacker thinks that the modified image is the same as x0, but the human perceives otherwise. An example of this in this particular figure is x2. Let me show you these errors happening in practice now. So here, the distance metric we are using is the infinite norm with a threshold of 8, which is popular in literature. So what we're showing here is that the original image is correctly classified as cat up to an infinite norm distance of 8 along a particular direction. The image is still correctly classified by the same neural network. Then an attacker or defender might think that, okay, along this particular direction, we cannot actually fool a human. But it turns out that humans actually start noticing the change along this direction at an infinity norm of 35, where by which time the level of that particular image changes to lengths. So it is actually possible to find an attack along this particular direction. This is an example of, again, the type 1 error. Similarly, we have an example of type 2 error here. Here we are using a panda image. The classification of this image changes pretty quickly. And humans, interestingly, start to notice this change from an infinite norm of 4. So an attacker who uses a modified image, say at an infinite norm distance of 5, might think that, okay, this particular image will not be detected by humans, actually will get caught. So this is another potential issue that can happen when we are using an incorrect perceptibility measure surrogate. So the goal of this particular paper was to test the appropriateness of popular measures used in practice. In particular, we wanted to see if we can quantify how good a particular measure is. The measures that we tested here are pixel p-norms, then arc movers distance, which is the minimum cost of converting one distribution to another distribution. Next, we had structural similarity measures, which considers luminance, contrast, and similarity of local structure. We used a window size of 7 without Gaussian weights for this case. And since SSIM is a similarity metric, we actually used 1 minus SSIM as our distance metric. And finally, we used p-norm of DNA representations. Here, we extract the embedding of the last hidden layer of a neural network. For our experiments, we used Inception V3. Now let's look at our study. A natural image is represented by x0. A particular direction is represented by v. We define a particular ray along this direction using the scalar a. Note that a must always be greater than 0. This indicates that a larger value of a means that the modified image x is more different from x0. We want to find a threshold AV along this particular direction v, such that the average human notices the difference between the modified image and the original image when a is greater than AV. This is known as just noticeable difference, or JND, in psychology literature. A distance measure in our case is notated by D, and the adversarial threshold is epsilon. Interestingly, we actually don't need to know the value of epsilon for our study. The key insight is that D is correct. If D is correct, then the JND image, the distance of the JND image along any direction must be a constant. Based on this, we define a condition number kappa hat. Let me explain what the denominator and the numerator are. So we have multiple rays for a center image that we explore. Along each ray, we find the JND and the distance according to a particular metric D. The numerator is the maximum value of all of these JND images, and the denominator is the minimum value of all of these JND images. Then, if D is correct, we should have that kappa D is very close to 1, barring some noise. If kappa D is actually huge, that would indicate that D is not a correct measure. Also, as noted, kappa D is actually dependent on the original image x0. Now let me show our experimental setup. For experimental setup, we used 3 popular adversarial images from literature: a panda image, a macaw image, and a cat image. For each of these images, we chose 10 perturbation directions. 8 were specially crafted ±1 perturbations. When I say ±1 perturbations, I mean that the support of these perturbation directions is non-zero, and the non-zero elements are either 1 or -1. The non-zero element is 1 if and only if the corresponding dimension in the original image is less than 128. Otherwise, it is -1. Next, we had two adversarial directions, FGSM and PGD. Let me show you the example of these perturbations in the next slide. So here I'm showing the 10 directions for the Macau image. As mentioned, the ±1 perturbations had 3 dimensions. First one was size, which was either small, medium, large, or extra large. Next, we had the channel of the image that we vary. That would be either red or RGB. And finally, we had the shape of the perturbation, which is either a box or a dot, where a box indicates a continuous box area that we change, and a dot means that we are changing random pixels in the image. The final 2 examples on the bottom right are the FGSM and the PGD directions. Based on this, we created our human experiment design. The humans were first given some instructions regarding what they're expected to see. Then for all 3 images and 10 directions, we had 30 trials and 4 additional trials, which I'll explain in a second. So for each trial, the human starts from the original image, the unperturbed one. Then they can gradually add a particular noise to the image based on the direction that is currently shown. Notice that for the green blocks, which are the ±1 perturbations, the maximum allowed perturbation step is 128. Beyond that, we ask them to submit the image. So the goal here is to tell them that submit the image whenever you notice a change or the JMD. But for FGSM and PGD, we actually tell them to submit the image as long as they cannot find any change or whatever. And then finally, we have the guard images. In this case, we have 4 unrelated images, which are used to find out participants who are not paying attention. In these cases, the change suddenly happens at a step size of 20. If a participant does not find this change, that means that he or she is not paying attention. We collected data from 68 Mechanical Turk participants. After removing the inattentive ones, we are left with 42. Now I'm going to show you some assessment based on the data we collected. First, we have the qualitative assessments. This is the particular graph format that I'm going to use. Along the x-axis, I'm showing the 10 perturbation directions, and on the y-axis, I'm showing the distance matrix. I'm going to show the box plot for each of these directions here. As you can imagine, if a particular distance metric is correct, then the median of these block plots should align. But as we will see, this does not actually happen. So here are the results for the 1 norm, 2 norm, 3 norm, and infinity norm. The orange lines represent the median of each of these box plots. So you can notice here that say, for example, we take infinity norm. Let's take 2 particular directions, say is red box and then M RGB box. In that case, the medians are actually at very different places. This indicates that this infinity norm for this panda image is actually not a good surrogate for human imperceptibility. Similar things can also be noticed for 1 norm, 2 norm, and 3 norm in these plots as well. If we look at the other remaining 3 metrics, which is SSIM, DNN, and EMD, we can also observe similar things, which indicates that qualitatively, none of these measures are a good representation of human imperceptibility. Now let's move to the quantitative assessment. Remember, we want to find kappa hat D, and if kappa hat D is close to 1, that would indicate that a distance metric is a good one. If it is large, then we'll declare that it is not a good one. So we estimate kappa hat D in 2 ways. First, we have the non-censored median. In this case, we discard the given up data. Remember, this is the case for the ±1 perturbations, where in some cases, the subjects might not find any change up to a step size of 128. Next, we estimate the JMD using the median. In the second approach, we use the first quartile. In this case, we do not discard the given up data. Instead, we consider them to be infinity and then estimate the JMD using the first quartile information. Now I'm going to show you the results for the quantitative assessment for the non-censored median. Here, I'm showing the kappa hat D values for the different distance metrics and the different original images. The lowest value of kappa hat D is highlighted in bold, which is 14, 11.9 and 11.2 respectively for panda, macaw, and cat. These results actually show that none of the kappa hat D values are close to 1, which indicates that none of the measures that we have been experimenting with so far is a good approximation of the human JND. Now I'm showing you the results for the first quartile approximation, where the infinity norm value is again the best for panda, which is 17.1. For macaw and cat, the 3 norm is the best, which are 5.7 and 7.6, which again shows that again, none of these values are close to 1. So none of these are actually good measures. The main takeaway from this paper is that we quantitatively show pixel P norms, EMD, 1 minus SSIM, and DNA representation P norms are not good matches for human perception. This suggests that adversarial attack formulation needs to be rethought. There are some limitations of our study too. First of all, we only used 3 centered images or 3 natural images. We unfortunately still cannot answer what is the correct distance metric D. We used a show, X0, and then perturbed approach. This is not a correct setup because in most natural cases, humans will not see the original image or cannot go back to that one. And we've also limited ourselves in the visual domains. In future studies, we want to address these limitations and then come up with a better measure of human imperceptibility. That would be the end of my presentation. Thanks for your patience. Feel free to ask any questions.
Thank you for the great presentation. We have questions from the audience. Yeah, we have the first question from Lina Huang. And Lina,
okay,
you can ask.
Okay, hi. Thanks for the interesting talk. So I just want to ask, like, how we land on the key insight that this good measure should form a circle, like we should have small condition number.
So we should have a if a distance metric is a correct one, then along any direction, we should find the JND at the same distance. If we are getting the same distance along each directions, then it doesn't matter what the maximum and minimum is. Both the maximum and minimum should have the same value, which would indicate that kappa should actually be 1.
Why is that? Because like I can understand like fixing any direction, then if there's like the GND things, but like you have different directions from a point X0. Yeah. So what the meaning like for different directions and why should them have the same?
I'm saying that humans are starting to notice a change whenever we move beyond a particular threshold. That was epsilon, right? Mm-hmm. So for a particular distance metric, that epsilon should be fixed. So the numerator and the denominator should always be epsilon. So we are actually.
But it's only for that direction, right? If we change the direction.
It's not for the direction. It is universal. That's why we are trying to find adversarial images along any direction that we can. And it should be on the boundary. The boundary should be fixed for any direction.
So why is that? It's like the feature of human observation or?
Yes.
Okay.
So that was the original the green boundary that I had shown. That was the weird shape.
Okay. And also like, I guess like here we want to compare all these measures like the P norm or all these things with the humans. So I guess human is the benchmark.
Yes.
Like I guess one good measure is that maybe like the ratio between the performance from human and the performance from the algorithm. Like why we don't use like performance like that?
Can you repeat that question once more?
Because we just want to make sure like the algorithm provide the same performance with the humans, right? Yes. This is the goal. Yep. So then we can use the ratio, for example, the ratio of the performance of the algorithm with the performance of the human. If the ratio is 1, then it's perfect.
Yes.
And then this is like a good measure. Why we don't use that? Why we should use this measure of small condition number?
Yeah. So here we were trying to show that we are showing a particular distance metric, how good or bad this is. What you're saying is another approach to show it. In that case, along multiple directions, we'll have multiple JNDs. Now, for the human case, how do we aggregate these values to show that a particular distance metric is good or bad? The ratio you're saying is again assuming that we already know what the distance is. So for pixel p norm, say 1 norm, I know that the threshold appears at 100, say. But what is the human calculating? What is the epsilon or threshold value for the human? We do not know that. So that's why we cannot do a direct ratio comparison between the human data and the metric that we are using. Does that answer your question?
Okay. I guess so.
But no, I have kind of a little bit of a deeper question. Okay.
Sure.
We know exactly how the visual system of humans works, right?
Yeah.
We have this since '62, and now we have very detailed models of the various levels. So two key characteristics are the humans, when they see and try to classify things, even in the front end, they use multi-resolutions. They look at the image at different resolutions. They also look all the time for symmetries. Okay? So you didn't account for that. So many of the attacks you describe, if you allow multi-resolution and searching for symmetries, they immediately go away. I have shown this. So why we insist on pixel level metrics when we know so much about the actual perceptual architecture of the vision system? What's
exactly? That's the question we are trying to address here.
There's a discrepancy here, right?
Yes, exactly that. So we completely agree with you, and we actually do think that we should be borrowing from those literatures. In this paper, we are trying to show that this is why we shouldn't be using pixel p norms. These are bad.
Because the classic example I give in adversarial attacks, and I think I'm going to hear it from the next two speakers, is you take the classic example they give on the stop sign, right? So I stick I stick a sign over here, and I make it look like 45 kilometers per hour. No human will be fooled by that.
Exactly.
Because the human will look for symmetry, will look at multi-resolution, gone.
Yep. I completely agree with you, and that's what you're trying to show. That
and
we shouldn't be using
I have a major complaint on that for many of the works on adversarial attacks, that they don't try to use the knowledge we have from vision. And there are similar examples from audio, but we discussed this some other time. Thank you very much for a nice talk.
Thank you.
Thank you, Yoan, and for the very nice presentation. And this concludes our session on cyber deception. And thanks everyone for attending this very exciting session. And now I will turn the control back to Dr. John Barris.
The next session is the academic panel, and this is going to be run by Radha Bhuvendran, who is here. And I think the speakers are here. So Radha, the floor is yours.
Thank you. So I'm trying to make sure that most of our speakers are here. That's great. Hai Fang is one speaker who hopefully he will join. First, welcome to all of you for the academic panel session. We have excellent participants. So I want to first introduce the panelists. And we have a structure that is interesting and I think forward-looking. I will also describe the structure of the panel. The panel members are going to be Professor Fei Fang, Professor Boli, Professor Haifei Zhu, Professor Tansu Alpchan, and then Professor Sukarno Metagona. Professor Fei Fang is an assistant professor in the School of Computer Science at Carnegie Mellon University. Her research lies in the field of artificial intelligence and multi-agent systems, focusing on integrating machine learning with game theory. Her work has been motivated by and applied to security, sustainability, and mobility domains, contributing to the theme of AI for social good. Her work has won multiple distinguished paper awards that I cannot list given the time. But she is one of the rising star faculty members who is joining this panel. The next one is Professor Bo Lee, who is an assistant professor in the Department of Computer Science at the University of Illinois at Urbana-Champaign. And again, along with Fei, Bo has a huge list of extraordinarily high quality awards for a junior faculty. I won't be listing all of them, but they pretty much are the key awards that you look at. Several of her papers, same as Faye, has won awards at the machine learning and security conferences. Both's research focuses on both theoretical and practical aspects of security, machine learning, privacy, game theory, and adversarial machine learning. She has designed several robust learning algorithms, scalable frameworks for achieving robustness for a range of learning methods, and a privacy-preserving data publishing systems. Her work has also been featured in major publications of societal interest media. The next one is Haifang. Haifang is holder of Alan Baston Assistant Professorship in Computer Science at the University of Virginia, where he also directs a Sigma Research Lab. He works broadly on game theory, machine learning, and algorithms, with particular focus on studying how incentives, information, data affect learning and decision making. Again, another faculty member with a huge number of awards, not only for junior faculty awards, but also research in the sense of best paper awards. He's well known in the community as well. The next one is Professor Tanshu Alchan, who is one of the founders of this conference and steering committee chair, and he has been a visionary in setting this conference and identifying the need for bringing games control and security and providing a community building framework. So he needs less introduction, but at the same time, I think it's important for us to point out that his book on network security, a decision and game theoretic approach, is one of the early foundational book that brings the areas together. It's game theory meets security as papers have come in. He sets the framework in that book with his collaborator and advisor, Professor Tamer Bashar. He also has another edited book in the framework of mechanisms and games for dynamic spectrum allocation, again with the Cambridge University Press that has published. Professor Alpshan has initially been at Germany as a faculty member in Tambe, and then he is currently a full professor at University of Melbourne, Department of Electrical and Electronic Engineering, and he is also a reader at the university. Next is Professor Sukarno Metagono, who currently wears multiple hats as a faculty member in the new School of Cybersecurity and Privacy, which is ranked the #1 in the computer science security field in their area. It's a very brand new school, but he's also Chief Innovation Officer for the Information and Cyberspace Directorate of Georgia Tech Research Institute. His background is in electrical engineering. He brings in and develops innovation techniques and concepts for GTRI. Before joining Georgia Tech, he managed basic and applied research in cybersecurity and complex software for Office of Naval Research. He has led the programs on several fronts, including TPCP, which is the attack surface reduction program of very significant scale. I mean, many of us, the top researchers in the cybersecurity and also formal methods have been key participants of this program. And I know many of these programs are very close tied to the DARPA agenda as well. He also developed the novel concept of next generation of fault-tolerant computing and somehow semantics agnostic methods called BFT++, and Learn to Reason, which is a program along with Crypto Factory, where streamlining crypto from inspiration to algorithmic, at least in the scope of problems that could be handled. Before ONR, he was a systems and chip architect and an entrepreneur in San Francisco Bay Area, where he worked on various chips and systems, such as embedded processors, switching fabric, network processors, and so on. With this, I am going to introduce the format of this panel. What we have are first 3 presentations of 10 minutes each from the Rising Star faculty members. We requested that they give talks in their emerging areas, which are exciting and broadening the game theoretic framework into social good and other domains, at the same time looking at the questions of whether AI and ML in games come in as interconnectors or application, or foundationally they can change the models and framework. So first, I request Professor Fei-Fang to start her presentation.
Thank you, Radha.
Are you able to share the screen?
Yeah.
Okay, great. So you have 10 minutes and I'll kind of manage the time.
Okay.
Yeah.
Sounds good. Can you see it?
Yeah.
Okay, cool. Yeah. Thank you all for attending this panel, and I guess it's my great honor to be invited. And I just want to kind of mention a few recent work from our group on integrating machine learning and game theory for cyber deception. I know that there are cyber deception sessions and a number of cyber deception related works at GameSec this year, and including 2 of our papers as well. So, but at a higher level, what I have been working on is that I'm very interested in those crucial societal challenges that we're facing, including physical security, cybersecurity, and also the mobility-related challenges, like how this and like these smartphone apps of ride-sharing has revolutionized our way of transportation, and then how can we make those platforms more efficient? I'm also interested in how to protect natural resources, forest, wildlife from potential attacks, and how to help address the challenges of hunger and poverty. And I'm taking this AI perspective, and what I'm trying to do is to use machine learning and computational game theory together to help provide some tools that can be used by stakeholders to tackle those challenges. And of course, today I want to talk about the cybersecurity part. And the idea of deception is just like looking at this car, which may look very crappy, but it is actually a brand new car with this rusty camouflage. And of course, putting this kind of camouflage needs effort. And the same and to take that energy for cybersecurity, we can view it as, okay, we have a number of systems in the network, and then each system has their true configurations. Some of them are actually like data servers, which can be very important. Some of them are less important. And then what we're trying to do is to provide this camouflage to these systems so that some of the unimportant ones may appear to be attractive to the attacker, so that we can induce the attacker to attack those targets. And as an extreme example, we have the honeypots. What we're trying to do is that clearly we try to make this honeypots to be the seemingly high attractive ones. However, if the attacker has any idea, has any awareness of the deception, then they may realize that, okay, if you have a system, if you have a network with 10 systems and only one of them is like extremely attractive while the others doesn't seem to be good, then clearly you may feel like, well, the one that is seem to be highly attractive might be a deceptive target. So that's why we need to have this game theory framework to kind of model these scenarios. So the first model we had as a joint work with folks from USC and Harvard and also Haiphong is the cyber camouflage game, where the defender's strategy is to assign a observed configuration for each system. So they may have their true configurations TC, but we can choose to assign them to a specific observed configuration, which may be different from their TCs. And a powerful attacker who is somewhat aware of the deception can know the number of systems with a particular true configuration and an observed configuration, but they cannot differentiate those targets with the same observed configurations. And then what our goal is to find the optimal assignment given feasibility and budget constraint. So again, consider a very simple example. If there's no budget constraints or feasibility constraints at all, now what would be the best strategy to do this camouflage if you have, let's say, 10 targets, 10 systems? Well, in this case, we can just try to make them all look the same, so that it's very hard, so that the attacker cannot get any information from the observed configurations. But when there are feasibility constraints and budget constraints, then the problem can become NP hard. And what we are trying, what we did is that we proposed a mixed integer linear program-based formulations for this problem to compute the optimal defender strategy. And then later on, we also try to extend the model for a more general setting. And from the simulation results, we can see that when we use this deception, the attacker's expected utility can be reduced by almost half using either the mixed integer linear program-based solution or a more greedy, heuristic greedy solution. So that's the first model. The second model that we were considering this is the social engineering deception problem. So in many cases, in some cases, the attacker would try to the attacker is targeting at a particular organization or institution. And then what they do is that they try to compromise websites that are frequently visited by the employees from that company or organization. And then when they can identify that, oh, this is a visit from that organization, then they will try to send exploits to that visitor so that they can steal credentials from that visitor and use that credential to compromise the company's system afterward. So for this kind of attacks, what can the defender do? The defender can potentially change their user agent string and IP address when they visit a particular website. And by doing so, one, it becomes harder for the attacker to identify that this traffic is from that particular organization. Two, it becomes harder to find send the right exploits to the visitors. For example, if the user agent string says this visit is from a Mac OS, while the visitor is actually using Linux system, using a Windows system, then the exploit sent by the attacker targeting at the Mac OS may not be like having any effect on the Windows system. So, however, if the defender always changes the user agent string for every website they visit, then it may reduce usability because some of the websites are designed in a way that the visualization is tailored towards the device used by the visitor. So then what the defender needs to do here is to trade off between the reduced usability and the increased security. So we formulate this problem as an optimization problem, where the decision variables are how much traffic to each website should be covered by the defender, meaning you need to change the user agent string, IP address, and so on and so forth. And the attacker model here is that the attacker would compromise some websites and scan some traffic for each website they compromise. And the constraint is that, well, both the attacker and defender need to operate under budget. And the attacker's objective is to maximize their expected scan uncovered traffic to the compromised websites, where the defenders is trying to minimize the attacker's gain. So by doing so, we have this, again, a mixed integer linear program based formulation, and then we use cut generation to improve the scalability. And based on this, we also developed a Chrome extension called CyberTwig, and that is publicly available for people to use. That's the second model. And the third and fourth model are the ones that are presented at the GAMESEC conference this year. So I'll just very briefly kind of introduce them. So the first one is a feature deception game. Here we assume that the attacker is kind of boundedly rational. They follow an unknown behavior model. The model is something like this. So for each system, they have a number of like configurations, and we view them as features. And we assume that the attacker has an unknown function f applied to these features that it leads to like how promising this target is. And we call it a score function. So, and then the probability that the attacker will attack a system I or a target I would be proportional to this score function. This score function can be approximated using a neural network, or maybe, or it can take other forms. And our goal here is that the defender needs to learn the behavior model from the previous attack data and then plan the reconfiguration of the targets. What we found is that, in fact, if we consider a single layer neural network as approximating the score function, then we only need polynomial number of samples to learn that behavior model, and the optimal reconfiguration can be found using mixed integer linear program. So that's kind of the third model. And the last model is this deception in the attack graphs, where we consider a very abstract version of the attack graph, considering modeling as there are a number of nodes, and the attacker is choosing a path from the access points to the target point. And the defender can deceptively add or hide edges and change target values. It doesn't mean that the attack graph is actually changed, it's just the appearance has changed. And then the defender, in addition to these deception actions, the defender can also allocate resources to, say, protect an edge. That is, if the attacker tries to move from a node to the other node, and if that edge is being protected, then the defender can successfully intercept that attack. And what we propose is to use mixed integer linear programming and neural architecture search to find the defender's optimal strategy. The neural architecture search is actually an AutoML technique, and we find it surprisingly work quite well in this context. So yeah, with that, I would like to end my part, and Redhard,
yeah, great.
Do we have time for
thank you,
questions?
Faye, and we will take those things later. Now it's Bo will share. If you stop sharing, then Bo will share and present her work.
Okay. Yeah, let me share my screen. Hello, everyone. I'm Bo Li from UIUC. It's a great honor for me today to. Hey, do I share? No, let me see. Okay. Yeah, it's so everyone can see the screen, right?
Yep.
Okay, great. It's a great honor to share my research, part of my research here with everyone. So mainly I'm working on adversarial machine learning, which is at the intersection of security, privacy, and machine learning. So basically, we can see that as a very brief introduction, we know machine learning currently has been ubiquitous in the world, which has been widely applied to different domains, including autonomous driving, intelligent medical treatment, smart city, etc. But the main concern is that we can see even such very powerful machine learning techniques has brought us a lot of security and privacy concerns. For instance, in 2016, this is a real example, right? In 2016, the White House Associated Press Twitter account was hacked via phishing emails, spreading the rumor that the White House has been attacked, which actually triggers autonomous trading bots to dump a large amount of stocks within seconds and swipe about $136 billion. So this really happens in the real world. And of course, from the privacy perspective, a lot of biometric recognition systems have been deployed for safety screening in the airport and at different places, which raise a lot of privacy concerns. So basically, as a quick summary, my research really focused on, even though we can have a lot of good machine learning platform and pipelines and tools, libraries currently to develop convenient learning algorithms and systems. As a typical machine learner, we still have a very hard time to develop robust and private algorithms and systems. So on the high level, we briefly talk about two things today. One is from the attack perspective, like the attacker here, what can be the potential attacks in the real world, and what's their strategies, and try to understand from the attacker perspective, so that we can develop robust defense algorithms targeting on those attacks and based on their utility and cost functions to explore their adversary limitations. So one thing at the first I want to bring up is why or what's the actual fundamental question in adversarial machine learning. One of them, I think, to me, is one of the most important one is in traditional machine learning, usually we assume that the training and testing data distribution are drawn from the similar or even the same distribution, right? That's why we can train from one and make inference from another. However, in the adversarial scenario and the environment, either the training data distribution can be manipulated. Usually we call it poisoning attack. We call it in deep neural network. It's surprisingly easy to do the backdoor attack, which means during training, you inject arbitrary triggers you have, and during test, as long as you have this trigger in any testing data you have, you can do whatever you want, like fool the machine learning model to make arbitrary wrong predictions, which is very surprisingly but very dangerous, right? And also the test data distribution can be also manipulated, which is called evasion attack, meaning if you train a good machine learning model and you can protect the model architecture, parameters, everything. For example, you have a spam classification or malware classification filter, and I do not tell you the model itself. However, the adversary can manipulate their testing data, for example, malware, a little bit to evade your model, even though they have no knowledge about your model itself, which is, again, still very dangerous. And here I want to give some examples of some such attacks and introduce 3 principles that we may follow and currently I think are the most important to develop the robust algorithms against such attacks. So the first is one type of physical attacks, which actually John also mentioned. I want to have a quick discussion on that later on as well in the talk. So basically, one is that we see autonomous driving in real world is widely deployed and people are excited about it, and we are very anxious about the security problem of it, right? And here is a real world stop sign taken near Vancouver and Berkeley, and we can see usually there are some graffitis and random patterns on them. So this makes us think, what if those patterns are actually adversary, right? And the human will not think this is dangerous and will not replace the sign, but the sign will actually mislead the machine learning models or autonomous driving vehicles. And to generate such physical perturbation, there are additional challenges. I will not go to details, but we can see, compare with digital one, in the physical condition, we have different angles, distance, lightning conditions, which may slightly change the pixel values and make the attack not that effective, right? And also from the last talk, we see from the student that say the perturbation should be imperceptible based on different LP distances, right? But we can see in real world, we cannot make it invisible. Otherwise, the camera cannot capture that, right? And also in real world, we also have different fabrication errors, like something you print want to be red, but turns out it to be orange or pink. And we can only add the perturbation to the object itself rather than the whole image, including the background in physical world, right? So regarding these additional challenges, I want to go to details, but we'll see we can generate a certain spatial constraint perturbation, which will constrain your perturbation into certain regions, which will of meaningful shape. And also we make sure we can sample from distributions like expectation over distribution, so that the perturbation itself will be effective under different representative distributions. So these two are the key factors. Basically, just to quickly go through. So basically, we have an instance, we add a perturbation, and we hope the whole loss can be fooled into this adversary target, right? But under different condition distribution, we hope this perturbation can be effective on the different representative distributions on the different conditions, and this whole big loss function can be combined with a mask, so that in the end we can see, I think some of you have seen such examples that in physical world, under different conditions like distances and angles, these types of all the stop signs in this slide look like reasonable and natural to human, but they will be misrecognized as speed limit sign 45. And similarly for this right turn sign will be misrecognized as stop sign, meaning that your car will suddenly stop at such adversary sign. And one interesting dynamic example is that on the left-hand side, you can see when the car driving by, this stop sign consistently be misrecognized as speed limit sign, even the car is moving under these dynamic conditions, but the control experiment always recognize it as a stop sign. And not only these types of classification models, but also object detection models, that you can see this stop sign can never be recognized, even though other objects in this room under different conditions can be correctly recognized. So this is a powerful of such attacks. It's not rendering your whole algorithm to be meaningless, but it only attacks the target, which will make it very stealthy and hard to detect, right? And another example I want to see is that even not only white box, as we mentioned, but also black box, like if you do not have your machine learning model, you just transfer the same attack generated by model A or against the model A to model B, which is of different architecture, parameters, training data even, and on the different environment, the same perturbation you can see against the different model. This is fast RSCN and the previous one is YOLO. And you can see it never recognizes the stop sign itself until you get so close, which is very late for the car to stop, right? And also very interesting, this example is actually exhibited in the Science Museum of London, and it shows that as a community, we already recognize that such vulnerabilities of machine learning models are very important and dangerous, and we should pay attention to that. And very quickly, I want to show not only such planar objects such as road signs, but also the real world 3D objects. For example, like here, if you optimize, this is a benign object, and from this as a starting point and optimize the 3D object as a little bit weird shape, and we 3D print out this shape and put on the railway, like highway, to test the LiDAR systems of autonomous driving vehicles as a 3D object. Again, similarly, we can see that this is an example for this is adversary object. In the LiDAR result here, you can never recognize this object from the LiDAR. So the LiDAR exactly ignores this object and then recognize it as an obstacle. But for a control experiment with a box with similar size, you can see the green box here, meaning that the LiDAR always detects that there is an obstacle and you should avoid it. So this means even like not only camera, LiDAR, and also sensor fusion, there are more examples. If you are interested under different conditions and different sensor fusion, we can see the models can be vulnerable as well. And to summarize the attack part, I would say not only like generative models, classification models, object detection, or even like NLP image, also like the trained RL machine learning models, different components like from the observation part, from the action part, and from the environment component part, they can all be vulnerable. So to my research experience, there is no model that I find is hard to attack and unable to attack yet, which is very unfortunate. And this is an example for the simulation for color that if you change the environment dynamics and the car, which is the body mass of the car, which is very realistic to change, right? You can put some heavy thing on your car and change the body mass, and the car targetedly hits the wall in the end, which is the adversary goal. So in terms of a quick summary, is saying that attack is very feasible without doing additional things. It's very hard to improve the robustness of the machine learning models. So another bunch of my like research is focusing on how to improve the robustness of machine learning models, right? And we can see there are many work proposed in terms of detection, defense against those attacks. And also there are big two trunk. One is certified robustness, which will provide you guarantee under small region of perturbation, and the other is empirical perturbation, empirical defense. Unfortunately, most of the empirical defense have been attacked again by adaptive attacks. And the limitation for the certified robustness is that the certification is a little bit limited. So that is to say, for example, here, only the certified robustness within later 2 or 3 years. This is a big bunch. One is from deterministic, one is from probabilistic perspective, and with all kinds of different relaxations. And this is an example. We built a leaderboard with all the with all the algorithms implemented, so that you can run all and compare with your own algorithm, which you can later on click the link and find all the algorithms. I will not go to details about that. So to me, I would say one potential reason about such vulnerability is that current machine learning models all view the are all like a kind of pure data driven learning process, which is there are a lot of information not modeled by the data that we cannot capture. So just as John said, you know, for human, there are some knowledge. We know there is if there is stop, if this is octagon, then this should be a stop sign, but machine learning model cannot capture that. So in my research philosophy in terms of the defense is at least the 3 dimensions. One is from the game theoretical perspective, how we can model the dynamics between attacker and defender as extraordinary knowledge into the learning process, so that we can improve the robustness. As just Faye gives an excellent talk about game stackable game, and for this adversarial strategies, we can also incorporate like what's the distance or perturbation that attackers can manipulate, what's their utilities, so that we can incorporate to model the dynamics between the attacker and the defender. Basically, we want to do this, optimize this attacker strategy. So here we all view the attacker as an oracle, and what's the mathematical way to model this oracle will be the research perspective, which I will not go to detail, but if you are interested, I can point to you some literatures that in our group. And another perspective, first is the game theoretical way to incorporate knowledge between the dynamics of attacker and defender, right? And second is there are some statistical knowledge or information from data and machine learning models. For example, in say semantic segmentation, there are some spatial information we can leverage. If you add perturbation, you on purpose break the spatial consistency, which is very hard to fix for attacker. And as a defender or good guys, for us, we can actually leverage that. And very quickly, we show an example that in the semantic segmentation, if you like sample 2 overlapped regions, and then you predict the overlapped regions for the benign one, because it's overlap, right? The results are very close. But if for adversary one, the prediction for the overlapped region are very different, and it's very hard for attacker to fix that, because if you look at this, the perturbation is very invisible and it's a perfect attack. So by this, it's actually possible to detect the adversary perturbation with almost 100% AUC detection. But this is limited to tasks or data that have spatial consistency information or spatial dependency. And similarly, you can see, you can also leverage the temporal consistency, like for videos and for audios. I will not go to detail, but from some quantitative result, you can see if you want to detect like adversary frames within a video, it's also possible to almost do 100% detection rate, but if they have the like a temporal consistency, right? And similarly for audio, you can cut and compare their consistency. If it's benign, their consistency is very high, and if it's adversary, it's very low. And therefore, we can do a very good job in terms of detection of such adversarial behaviors. So this is a second principle to identify or discover those additional statistical knowledge from the machine learning and data to identify and improve the robustness. And the third one, which I think is the most interesting but the hardest one, is human knowledge. To incorporate human knowledge into the learning perspective. For example, in this one way to incorporate human knowledge is to use, say, statistical graphical models, right? Like we can combine different neural network. I call it as a sensor models, which can be easily attacked, as we discussed. And then there is some reasoning, like human can reason, like human can learn, have experience, and we can incorporate such thing into the graphical models. Say if my neural network 1 tell me it's a dog, and the neural network 3 tells me it's an animal, then based on the knowledge, I know dog belong to an animal, so I know kind of they are doing the right job. But if the first one tell me it's a stop sign, and third one tells me it's an animal, then I know must one of them is attacked, right? And it's very hard to attack all the sensors in a consistent way that can still satisfy the knowledge you have, right? If you can do that, like as a defender, we have no way. So based on this, actually we can do some thing to like improve the robustness against the, say, the stop sign. So basically you can compose, I don't have detail here, but you can compose, say, one sensor machine learning model to detect the shape, one detects color, one detects the content and different things, and combine all those knowledge together. So one thing I think currently why people haven't done this in terms of robust recognition for the road sign is that if with single neural network, it's really hard. And we know such knowledge we can leverage, but we don't know a principal way to incorporate. I think the sensor reasoning, like pipeline here, use the game, like a graphical model to incorporate knowledge is a way to incorporate such knowledge. So yeah, with that, I will end my talk. And basically, I hope there are some principles from the both attack and defense perspectives that we can leverage and understand and improve the robustness of our learning systems.
Great. Thank you, Bo and Haifang. Please share your slides and go through your thoughts, and we'll start the panel after that. Thank you.
Okay, I'm starting to share. Okay, so can everyone see my slides and hear me as well?
We were able to see it for a second. Okay, great.
Okay, good.
Yeah.
Use slideshow. Okay. Okay, actually let me see where it goes. Okay, good. Yeah, so first of all, thanks. Thanks for inviting me. It's a really great honor to be part of the panel. I want to start by apologizing that for my slight delay. So I actually thought it's Pacific time 1 p.m. because I'm kind of communicating with Radha. I somehow by default thought it's the 1 p.m. on the GameSec website is the like Seattle time 1 p.m.
No worries, it's all yours. You can start the slides.
Yeah, so so that actually is an example of information asymmetry, which which causes a problem, and that's actually also part of the theme of my talk. In particular, I'm gonna share some of my works about understanding the strategic role of information in the so-called security game model. I'm sure that in this, during the entire conference, you must have already learned that security is a global challenge. There are many kind of problems in both physical security and cyber security, where we need to defend against intelligent adversaries. So if you think about it, a common challenge among all these problems is basically there's a common problem is you're trying to optimize the allocation of a limited number of security resources in order to defend against some intelligent adversaries. Right? That somehow is a problem that underlies many of the kind of security problems that we're thinking about. And the so-called security game model is basically just a kind of basic stacker game model that try to capture the allocation, resource allocation in the adversarial environment. So that's kind of it's kind of basic model. And so I think most of you probably already familiar with the model, but here's a really quick kind of brief introduction about this so-called security game model, where essentially there's a defender and there's an attacker. The defender only have a limited number of security resources, but he needs to protect a large number of targets. For example, in this toy example, let's say you have only one resource, but you need to protect 2 targets, right? If you protect target 1, then the intelligent attacker, he's gonna decide to either attack target 1 or 2. Of course, if you're protecting 1, the attacker gonna conduct a surveillance and figured out that it's not a good idea for him to attack one as well, so he can attack target two. So, there's a lot of study about how do you do optimization in this problem, but I think the really underlying most of this work, the key idea is really try to use randomization to achieve unpredictability, right? If you protect the target one, the adversary gonna surveillance it and then figure out that you're attacking target one. So a better idea would be for you to randomly, sometimes cover target one, sometimes cover target two, depending on the importances of the targets. And the key idea, again, is try to use randomization to achieve unpredictability. So now that the attacker doesn't know which target you're actually protecting for sure. And therefore, naturally, you could imagine that information becomes plays an important role in this procedure because, the unpredictability, basically your entire defense is basically built upon the assumption that the attacker is uncertain about it. So therefore, the entire interaction really depends on how much the attacker knows about you and how much you know about the attacker. So that is why information somehow is like an intrinsic factor in security games. If you think about the game I'm just describing before, the defender is really trying to hide his resource allocation information by using randomization. So now it makes unpredictable about where his resources are going. And on the other hand, the adversary is trying to extract the information through surveillance. He wants to learn where you are really going so he can avoid your protection. But this kind of competition over information in security really goes far beyond. So you care about the information, not only about the protection status of a target. You really care about the information about any possible feature of the target, right? Whether the target you care is important, or whether the target you care, can be easily attacked in the morning, or maybe it can be easily attacked in the afternoon. These kind of information are all important, and so both the defender and attacker are competing on those information. So that is why information really plays a kind of key role in this security problems. So, so there were kind of my research tries to address this kind of strategic aspect of information, basically from two relevant themes. The first one is I'm trying to look at if the defender is at an informational advantage of the situation, meaning he knows more than the attacker. Then how can the defender make a more informed decision due to the fact that he knows more? And how can the defender possibly deceive the opponent or deceive the adversary? Also, because he knows he has an informational advantage, because he knows more, that typically gives you the chance to play deception. And on the flip side, I also try to look at if you are at an informationally disadvantaged situation, then how can you be robust to uncertainties about things you don't know? How can you learn to optimize decision when you don't know the attacker or don't know the adversary? And finally, how can you deal with strategic or even possibly deceptive opponents? Because you know less than your opponents, you might be deceived. So how can you handle this kind of situation? So in the remaining of the talk, due to the time limit, I will just introduce two examples from my work, which give you kind of concrete idea about what each part could be about and what kind of results you can expect from these studies. So my first example is actually from a real world application where, nowadays it's actually pretty common now. People use drones to try to combat illegal poaching. So essentially the idea is that you're gonna fly the drones, and then if you detect the poacher, you will try to kind of stop the poacher. There's actually an NGO which is doing this, which is the Air Shepherd. So that's kind of NGO which really are doing this job. So due to this kind of advanced computer vision techniques, nowadays, when the drone is flying, it can have these drone videos where it can automatically detect the poachers. But the problem is we're trying to study is the next step, right? Now you are able to predict the poacher, but how can you interdict the poaching? How can the drone interdict the poaching? So particularly this is challenging because very often there aren't any rangers around. So even you detected the poacher, you want to inform the nearby ranger to come, but very often there were no rangers around because some national park is super large, and you are not able to cover them very well. So the idea turns out to be that you can use deceptive signaling, because at this point, when the poacher, when you detect the poacher don't know whether there were rangers around or not. Only the drones or maybe the defender knows that there are rangers around or not. So you can utilize this information asymmetry and try to deceive the poacher and make the poacher think that there are rangers around. So that's kind of the idea of deceptive signaling. For example, you can ask the drone to kind of flashing its lights or making some noise. But the idea here, the key thing here, that you don't want to warn or send such a warning signal always, because if you always do this, you're gonna lose so then it's don't have a deterrence effect anymore, because the poacher gonna just think, wait, I don't care. So whenever the drone sees me, he's gonna flash a light, but I know no one is gonna come. So therefore, you have to be very careful about your deception strategy. It have to be a half-truth, right? It don't have to be exactly true, but it have to be a half-truth. So this really raises quite a bunch of research challenges or research questions. The first thing is, how can you model such deception strategy so that the drone, mathematically, so that the drone can implement it? So we studied this we referred to a model called strategic signaling. And so then the question is, how can you coordinate the drones and the rangers? Because the problem is you're gonna hope there will be rangers around when the drone is flashing its light, but there doesn't always have to be. So you need to optimize this coordination. This problem actually turns out to be NP hard, as we proved, but we show that it actually admits very guaranteed approximate solution. And finally, because of this drone's detection is very inaccurate due to this computer vision algorithms. So you need to handle the inaccurately sensed information by developing robust solutions. So this hopefully gives you an idea about how you can utilize information advantage to do a better defense. The second example I want to share is basically try to learning from when you're at an informationally disadvantaged situation. So for example, you don't know the attacker. How can you learn the optimal play by interacting with the attacker? Because very often in many applications, it's not clear who are the attackers, how rational are the attackers, what are the utilities. Therefore, a natural way you can learn is you can try to learn from the attacker's interactions. You can learn from by interaction with the attacker. If you play this strategy, attacker responded this way. You play another strategy, he responded differently. By such repeated interaction, you can learn your optimal strategy. And if this turns out to be indeed doable, if the attacker were honest, in the sense that the attacker can honestly best respond to your strategy or follow some kind of model honestly. But what if the attacker is trying to deceptively react to your learning algorithm and try to mislead your learning algorithm? And a recent result by us showed that if the optimal attack deception in this case actually always try to pretend to be completely against the defender and try to make the game zero-sum. So that's kind of a negative result, showing that you actually are not able to learn anything from the attacker when the attacker is trying to deceptively react to your learning algorithm. Because at the end of the day, you're gonna learn that the game is zero-sum game. You're gonna just learn the minimax strategy. You don't learn anything specific about the attacker. And note that this result actually only holds for security games. So it depends on the protection and the attack structure of the security games. Actually doesn't hold in general. So that means this kind of security game, this resource allocation structure actually does lead to difficulty in learning. Some remedies you could study could include, so you can leverage more prior knowledge about the attacker in order to do a better defense so that you can learn more accurate information about the attacker. Or maybe you can assume that the attacker is also uncertain about the defender. In this case, the defender also have some information advantage and hopefully can do better. I just want to conclude this talk with a saying by Napoleon. So war is 90% of information, I guess. So many of the problem in the security is like a war it's like a mini war between the defender and attackers, and information really plays an important role there. That's all I want to share.
Great, thank you. You can stop sharing the screen. So now I thank all the presenters, and we return to the overall panel for you to directly ask the questions on the chat channel or raise your hand and pose the question from audience. for the engagement part. I do have my own questions, but I want to make sure that participants who have raised their hand are able to ask. First, Dr. Charles Kamoa is there, and he has a hand raised. Charles. Okay, we cannot hear Charles. You may be muted. I see Andrew Clark's hand raised.
Oh, yes. Hi, can you hear me?
Yeah, we can.
Okay,
yeah,
good. Yeah. Yeah, I had a question for Fei Feng, I think the first presenter. One of the methods that you mentioned consisted of adding edges to an attack graph. What are some ways this can be done in practice? And do you account for the fact that you may not be able to really say with certainty what the adversary's attack graph looks like and whether you are successful?
Yeah, so there are two questions. So the first one is what actually corresponds to adding edges in the attack graph. So for example, if you consider even just adding honeypots, then what you're doing is that you add a node in the system and then you need to link this node with other nodes so that it feels like you can compromise that one through some other machines. And that could be just one way of adding a fake edge. Well, but on the other hand, you can also view that as you're just adjusting the target value, meaning you know that there is a target in that system, which is indeed there is a target in the system. It's just that the actual value is 0 and then you make it appear to be high valued. The other things that might happen is that, okay, you have some ports that are actually closed, but you can try to make it appear to be open. And then that may lead to some attackers believe that they can exploit that to send to compromise the system, which they cannot actually. So that could also be viewed as a way to adding fake edges. And the second question is, what if the attacker doesn't really observe what we present to them? Yeah, so in our current work, we're actually only considering two extremes. One extreme is to say the attacker is kind of quite dumb. They believe whatever we are presented to them as we planned. And the other extreme is that the attacker actually knows exactly the underlying attack graph. They can ignore all the camouflage. And we're considering like a mixture of these two types of informants. But we can imagine that as an extension, we should consider this like various types of attackers, and then to model their beliefs of the perceived graph. And also, we may even consider this like sequential attacks, and then we can infer their perceived attack graph from their actions. So those are the things that I can think of as for now.
Thank you, Fei. The next question comes from Charles. This is to Haifeng. He's asking you about the last part of the two examples you gave. What if the attacker does not know the defender payoff?
Yeah, thanks, Charles. That's really excellent question. So yeah, exactly. So our negative result is built upon the assumption that the attacker have absolute information advantage over the defender. In a sense, the defender knows nothing about the attacker, but the attacker knows everything about the defender. So, and unfortunately, there's a negative result in that case. So it's a very intricate and open question that if the attacker or if the defender also have some information advantage, that is, there's something about the defender the attacker does not know, is it possible that for the defender to learn a better defense strategy? It's a very interesting question, and I don't think we know the answer yet.
I have one question for both Bo and Tansu. I think it intersects both of you. Bo raised a question in terms of machine learning, assuming the stationarity is not a good idea. And I think it reflects well with the adversarial interactions with the system. stationarity is not something we can buy in. But if you want to formulate the games and look at studies, what kind of reasonable models can we take with the data?
Yeah, that's a good question. So I didn't go to detail for the game part. Basically, for example, if we form the interaction between the attacker and the defender as a game, so the defender would be actually the leader, the attacker will best respond for that. And in the end of the day, as a defender, we want to find the optimal strategy considering the best response of the attacker. So the formulation will look like the defender is minimize the loss based on all the data, like just training traditional machine learning models. But this data will separate into benign and adversary. Those adversaries are the target of the attacker. Then we will incorporate the attacker manipulation strategies into this consideration. So the defender essentially is trying to solve a constraint optimization. The optimization objective is still minimize the loss, but the constraint is considering, say, the attacker will manipulate the malware this way, so and they have certain budget, they cannot say manipulate up to k functions or k sequence, or they have a distance function to regularize how different the manipulated malware will look like with the benign distribution. And by doing this, we kind of have the double oracle in the inner loop. We find all the potential adverse constraints and add back to the defender's optimization and try to minimize over the potential constraints of the attacker.
Thank you. Tansu, you want to add to this part from the game perspective?
Game or machine learning perspective as well.
Both,
Thank you.
Mm-hmm.
It's a good question. Actually, it kind of I think falls under the umbrella of transfer learning as well, because you're looking at one type of data set and then try to transfer it to another one when you lose that stationarity between the training set and test set. And I agree with Bo that that's one possible direction, is trying to robustify the learning process. But it's a hot topic, and how do you do transfer learning? It's been actively researched. So we have been recently looking at in the area of smart grids, trying to learn how for example, the distribution grid works when you have a normal situation, and then can we make predictions about the future based on that when we embed batteries, electric vehicles, and solar panels as they penetrate more to the customers on a street level. So that's also a similar situation. Adversarial will be the similar, of course, when you train on maybe clean samples and some simulated attacks, but real world attacks will be looking quite differently. Can we generalize towards that? Yeah, that's a very good research question and direction.
Other question I have, I'm sure John and others have question. One more is that if you look at most of the things, we are arriving from the data and also linking AI ML to games from the application domains. That seems to be arising in most of the problems. Where do you see where the techniques directly contributing to the advancement of the games themselves, theory side? I mean, reinforcement learning and other things have been used in certain contexts, but with lots of new tools coming in from the AI ML side, what are your thoughts on this space? It's for any of Kano or the panelists. Anyone can just.
Okay, let me see. Right. I mean, so this is basically the connection between machine learning and the game. So there is two ways that I can see it might be more. One way would be to model the training adversarial on the machine learning itself as game theory. The other one is to use machine learning to help some situational or adversarial situation, right? Basically, the AI basically work as a surrogate of the user or the player, maybe, or sometimes as they helping or or additional tool to the user. And this includes some of the one that has been talked earlier about using AI using what you call using reinforcement learning to kind of adapt the AI. And this actually create a potential problem, right? Because now your AI is actually learning from the data of your adversary. And there are, I don't know how to formulate that, right? That has to be formulated because if you are going to adapt your AI, you are actually learning from your adversary, some of it, right? And how much can you learn? How much is it a deception? Yeah, I don't know. There are so many interactions that aren't that can be derived from the interaction between AI and game theory.
I would like to add on top of that. Yeah, I fully agree with Carno. So there are two sides of the there are two elements, right? And they feed to each other. Like in GANs, game theory can be used to analyze the learning processes, both in adversarial and non-adversarial settings. And in flip side, there has been these great successes by OpenAI and DeepMind. How do you solve large-scale games with AlphaGo type of in limited environments, but they were still large successes in conquering complexity and scale of the decision-making process. So I'm very optimistic about AI ML usage in game theory, especially in security games, both for identifying the parameters of the game from data, that's one direction, and then also to solve the large-scale complex games. And I find it very exciting because it brings games closer to reality. When it comes to adversarial learning, one issue, and actually Carno mentioned the reinforcement learning, and you can attack reinforcement learning indeed by through deception. And we have a postdoc here in a project at Melbourne exactly working on that. How can we defend against it? It makes the problem much more interesting than these static adversarial learning problems. And I think they can be quite deceptive themselves. The community has this overemphasis on these image-based attacks and formulating it as static games in one shot without thinking the end-to-end system, right? A car recognizing a stop sign is not a static image recognition problem. Actually, it's throughout the video. It's ensemble learning, and it is maybe built-in robustness into it. And I would love to see our community move on from static games that were maybe state of the art when I wrote the book, but to dynamic games, handling the complexity and taking into account the context and systematic aspects, end-to-end system aspects of the problems, and then the solution of those dynamic games may look quite different from the static games, and the strategies may give us much more insights about reliability or unreliability of AI methods, and allow us maybe to engineer much more robust solutions, building upon the nice presentations made today, moving it, extrapolating it to the future, maybe 5 to 10 years. But overall, I'm maybe overly optimistic that AI ML may change the names, but will be there with us, and that they will continue to play a significant role also in security games and I guess in GameSec community.
So I have to make some comments. Okay, so this is to all of you. And if you know me, you know this question is coming. You all talk about AI, but you don't define it. And AI is not just machine learning, right? In order to actually define something as AI, you must include knowledge, representation, and reasoning. Just think about yourselves. When you do something, you learn things, but you don't just learn them. You create concepts, you connect them, and you use these concepts in conditioning, and so on and so forth. And I'm very disappointed, not in you personally, but in general in the field, that I have not seen more effort in developing knowledge representation and reasoning and linking them to machine learning. There's only one area that this has happened, And you all know the results. This is in natural language processing. Everything you enjoy from Alexa and everything else, automatic translation, is because of that. Now, particularly in the field of security, this is particularly important. Why? Because only a stupid attacker will do the same thing many times. So in machine learning, the typical challenge we have is we don't have enough data to train. So we have to learn to live with small data. And this is precisely where if we had a knowledge graph or an attack graph or something like that, it can be very useful. And my last comment is, if you take that approach, then you actually end up with some very interesting games on graphs and different representation and dynamic games and all that stuff. For instance, Bo, I mean, in terms of the, I think it was you, right? In the stop sign, okay? The reason I am not going to be fooled as human is, as Tansu said, because I'm not just sitting there looking at it, I'm going around. So I use what is called, aspect graph in different resolutions. And I immediately, my brain uses the background and say, it cannot be a stop sign because it's not symmetric. I'm not even thinking about that. It's because I have a library of instances and I very quickly identify things. In other words, I have a knowledge graph or knowledge representation reasoning and I use it with my machine learning. And I would like very much to emphasize this needs to be done in this area. There are two things we're looking at, in case you have heard them, that they offer promise in terms of working with small data. The one is called hierarchical temporal memory, that it has been proven particularly successful in attacks, but again, it has not linked to knowledge representation and reasoning. And the other is, reservoir computing, because this also has shown that with very small amounts of data, you can predict. It's not the answer, it's just a different, a little bit direction from the traditional machine learning tools. So basically everything you described and all the weaknesses you described, it is a problem of the machine learning algorithms we're using. So we have to change them, okay? Thank you.
Yeah, I think to follow John, I agree. But I also say that both presentations hit at the core of some of the aspects of the problem here. Attacks don't come with any distribution whatsoever. If that is the case, then we would have taken care of it a long time ago. There are different types, and then as John points out, each of the attacks may give you certain types of small set of data. And so I have seen people using GAN, adversarial GAN and other things for actually CAPTCHA, breaking the CAPTCHA, the small data set and the synthetic data set. But if you go into a broader class of attacks, I think the non-stationarity and lack of being able to draw from a distribution keeps us away from the strategies that speech and language groups have been able to use for recognition and building the backend network and using human to train those networks. There's a lot of engineering that goes behind, because in our department, along with the computer science, people did actually work on this Alexa problem for constant communication, and they actually won the first Alexa prize. But behind that was a lot of manual work. It's not just the automated natural language process. And I think the point hit by both John, Tansu, and I would say the whole panelist comes to the point that its process is non-stationary, we agree, and transitions are also difficult. But how do we go about learning some of this? Tamer is here, he's not in the panel, but he actually has used adversarial learning to actually improve certain things for reinforcement learning. And so they use that to minimize some instability problems. And these are papers Tamer's group is looking at for helping with the control aspects of the problem from the perspective of adversarial learning. So maybe if Tamer wants to say some things, okay, go ahead, please.
If I may add to the, because John actually touched a point that's close to my heart. That's actually my dream of, figuring out for the Navy until the end of my career, is bringing together the two fundamental strains of the maybe AI, if we can say AI in general, is the connectionist machine learning data-oriented approach and the logic approach, right, and reasoning. And we have game theory use a more symbolic reasoning approach, and then now we are experiencing arguably the peak of data-oriented connectionist approaches with the neural networks and reinforcement learning and everything. For me, the holy grail and my dream is to bring them together. But for that, as John said, you need the new computing architectures. That's easy to say, actually hard to do, but it's a deep, hard problem I would encourage all young colleagues to look at. Don't stick just with the fashionable machine learning and try to solve the problem within that sandbox, right? We need to go beyond the sandboxes and go a bit more untraditional. And some of the questions that you sent me, Radha, was what would you advise to graduate students in the field? I think we should be more adventurous and stop doing this whole incremental work of following the crowd. And okay, this is the fashion of today's data-oriented machine learning, and the soft side of the downsides of the machine learning in terms of the adversarial learning. But if we stay in that sandbox, I don't think we will find the answer there. I fully agree with John. We need to go back to the models context where humans actually use very strongly, and you cannot have context without logic and reasoning. And I strongly believe game theory provides us the umbrella for that, to build that context and bring the logic back to learning and back to AI.
Actually, as I said in Stockholm, you may remember it, right? And that made Tambe very happy, is that game theory provides the semantic theory for many of these things at a very fundamental level. Many logics actually can be understood from game theory. Forget the application. This is a statement about what is the universal computational model, right? I made that statement in Stockholm, and I'm working on that. So that should be very encouraging for a conference like this. And the second encouraging aspect that I want to tell young people, this particular area of security is very difficult, but very challenging, because it pushes you, right, to look at new ways. Because if you go the traditional way, you will find all the problems you're describing. You have small amounts of data, you cannot have infinite memory, you have to act quickly, all that stuff. All this is part of security. So this is a very wonderful area to try to exploit, right? New approaches, new methods, and so on and so forth. More so than, how do I learn to recognize 5 numbers or 5 images? Please, folks, get away from MNIST, work on other data, right? I mean, we would like to be able to extend these technologies to data that they are not images, other things, right? This is where the challenge is.
I think that is reflected in the selection of the rising star faculty we have. I mean, in fact, Bo points out that looking at the sensor fusion, looking at multimodality, even if you are coming from signal processing or the background, you can help to move forward. And Haifang's work as on the bounds and other things are equally important, because even if you can't go into the logic mode, can you provide guarantees for what you are doing? Because I want to be able to become comfortable with what is being computed and what is given. Is there a way for computationally at least guarantee, even if we can't explain all the details? So those are, I think, some challenges.
So explaining, right? Explaining the result of machine learning. I mean, there are a lot of programs being done. DARPA put a lot of it, but fundamentally, it's not solvable without logic. Here is the reasoning, right? So how do we explain stuff to human? We explain stuff to human using language. Language by definition is formal. As such, you have to be able to bridge statistical, which is all of the machine learning, the current range of machine learning is statistical, into logic, which is reasoning. If you cannot do that, you can never explain. On the other hand, I mean, if the application is image processing, you can somewhat explain, because you can just say that, oh, well, this layer, it looks like this, the other layer looks like that, but you really don't explain. It's our eyes that does the explaining to us, because the problem is image. But if the problem is not something that can be visualized, that thing is lost. So this is So in the end, AI will not move forward if everybody just looking at it from connectionist point of view. This, I mean, I have written about this. This is part of learn to reason concept, basically making an analogy of statistical method of machine learning as our gut feeling, and all of the formal method of logic as our deliberative thinking. We need both. And even when we think that we think logically, we actually use statistical to bring weight into that statement. But if it, but anything statistical can only work if it is about perception.
No argument there, Sukarno, but the statistics we need in some of these problems, including intrusion detection, I will call them small data statistics. And these are very different than the usual statistics that people use. Very, very different. No argument with you that we need all kinds of statistics, but the one that I see missing, especially in intrusion detection and security, is small sample statistics. Okay, these are very different. These, for instance, have the mathematics are there, but people are not using them. You have to start learning about, tail distributions and large deviations and ray events and all that kind of stuff, right? And then you can put them back with logic, and you get very, very, very nice results. I'm with you. You need both logic and you need statistics. Neither of the two can do it. Okay. Hello.
So the problem with tail distribution is this is when I was at the ONR. The people that does machine learning at ONR, they basically during the big data, they are basically not interested in big data. They are interested on small data within big data, right? Which is because all of the social network all of those are all big data, but the one that are interesting for the military are actually small data.
Yeah, I want to add one more point, which is I agree with everyone about the discussion and especially for the reasoning part. And I think it's definitely important in terms of improved robustness and security by combining statistical and reasoning together. And that's actually one of our main direction in our lab, talking about representing first order logic into the machine learning statistical features and improve the robustness. But one thing I want to mention is that one big challenge, maybe it's benefit for the current researchers along this direction, is that the computation efficiency, because even we just solved the min-max game for, say, the graphical models from a small graphical models, it's a Shahin complete problem in terms of solving the min-max and get the certification for the robustness itself. So that's why we need to reduce the number of nodes, say, in a graphical model or in a certain logic representation structures. So that's actually a very interesting, because previously in the traditional AI, we may not need to solve huge large structures because we have limited knowledge. But currently, as John said, if we need to incorporate or consider big data, then we actually have a large amount of knowledge. We can automatically extract those knowledge from NLP, from image, from things. But then how to use them and compute them is actually very challenging, and that's a very interesting challenge, I would say. And second of all, not all knowledge are robust and helpful, I would say. And another direction we are working on is what knowledge, what principle satisfaction is defining the robust knowledge and non-robust knowledge. So if, say, animal include a lot of things, such knowledge is not that useful, but say a stop sign is an octagon shape, this knowledge is super useful, right? So what defines the uniqueness or the unique assignment of first order logic reasoning? This is actually one thing reasoning recently we are thinking how to define the robustness of knowledge. So I think even along this line, even though knowledge is developed for a long time, but currently if we leverage and integrate with statistical features and improve robustness, there are additional challenge and interesting directions that I think was a lot of thinking and a lot of open directions.
Mm-hmm. Yeah, I think as we come to the closure, any statement, Faye, you want to say anything from the social good side of the challenges?
Yeah, I completely agree that we will need to use logic and knowledge to help the to help us understand the world, or to help us to build AI-based models. And for us, since we work with multiple stakeholders to address real challenges like anti-poaching, we definitely need to learn from them what are the logic behind their decision making and planning the routes, and then trying to kind of incorporate them as knowledge into our model. To give you an example, previously they are asking us like what kind of routes are easy to follow, and then they told us that, oh, if it is like a mountain and then it is very steep, then you should follow the ridge lines. If it is not that steep, then you can take other routes. And then we need to convert that into, say, the secondary derivative. If that is high, then we should do this. If the secondary derivative is low, we should do this. So this is kind of like how we elicit the knowledge from the domain experts and incorporate that into our AI-based tools.
Okay, I have one more question for you. Since one of your diagrams showed hunger,
yeah,
how do you bring that to engineering table?
Very good question. So
because
with
this is something of a big struggle for lots of people asking engineering and computing community, saying that what can you do, because this is a real problem. Homelessness is a real problem. How do you where do you find the knob? Where is that place to turn it into engineering problem?
So at Pittsburgh, there is a food rescue nonprofit organization. And what they're doing is that they ask the restaurants or grocery stores to call them if they have food that cannot be sold anymore, but they're still good. And then they would try to match the donors, the food donors, with recipients, like the local community, like the shelters, or even the primary schools with students from low-income families. And then what they do is that they're not going to deliver the food themselves. Instead, they develop a smartphone app and then ask volunteers to help deliver the food. And then what we're trying to do is to really kind of optimize for their smartphone app operation. So we try to predict what kind of donor recipients this kind of donation requests can hardly be claimed by volunteers, because for those requests, we need the human dispatchers to take some actions manually to see what they can do with them. The other thing what we do is that we try to improve the notification scheme to the volunteers. You do not want to bother every single volunteer for every single rescue you received, and then how to strategically recommend those kind of rescue requests to the volunteers is something that we can do. And we have collaborated with them, and we have designed this new notification scheme, which has been deployed by them since January this year.
Hey, you should look at a program like that in Sweden, which is going on for 5 years. I happen to know because it's under the auspices of the Royal Swedish Academy of Engineering Sciences. Exactly the same model. You try to find food that has been left around, and you try to find needy people and use volunteers to distribute it. You may, if I find a web page about it, I'll send to you. But it started about 5 years ago from the Royal Swedish Academy of Engineering, exactly to help people that they don't even have to eat, so to speak, right?
Great.
Yeah.
Yeah. Thank you.
Yeah. So it may be useful to collaborate with them.
Indeed.
Great. If there are no other questions, I will hand the forum to John. You are muted, John. Okay, John is muted, so
you are too fast. You are too fast for me.
Okay.
I mean, are you in communication networks? No, you're not. So you don't understand delay in transmission, right? Or in queuing.
No.
That's okay.
So since I work in cyber, so speed is cyber.
Yeah, sure. You guys assume everything is available instantly, no delay, nothing. Very good. Now, we finished the session. Thank you all very much. It was very interesting, and don't worry about running over time. We actually could have the webpage until 2:30. Anyway, so hoping to see you tomorrow. All right, and we have two more interesting days. All right. Okay.
Yeah.
Thank you again very much.
Yeah. thank you, everyone, panelists, especially Faye, Bo, and Haifeng for preparing slides and also pointing out problems. Tansu, thank you for being up. I guess 5 o'clock, 5:20 now. Kana, thank you so much.
Thank you. Thank you for inviting us.
Thank you, guys. See you tomorrow. Bye-bye. Thank you. Enjoyed it.
Bye-bye.